Welcome to One Chemistry. We are seeing organic chemistry concepts. In this video, we are going to see organic conversions. It's a very important topic in organic chemistry. It involves so many concepts and so many strategies. More importantly, we are going to solve 239 problem completely. It will be help you to understand the organic conversion better. Stay tuned. What is inside this video? Basically, it contains the essential thing, that is what you should know before going into organic conversion. Fundamentally, it's a game, so you have to convert one functional group into another, then basics involved in the organic conversion, then rules, further reagents. These are the key factors to master the organic conversion. Finally, we are going to see 239 fully solved example. We will solve step by step every example with questions and answers. These questions are from various examinations and various books. So let us see one by one. First we will see what is organic conversion, what you should know about it, and basics involved in it. If you think organic conversion is the game, then you should know you are converting one functional group into another. Alcohol to halide, halide to aldehyde, aldehyde to nitrogen, aldehyde to nitrate, nitrate to amine, ester, acid, chloride, so on and so forth. Further, order is important. You are converting A to B, B to C, or A, C, P. There are many possibilities. Then you can do back and forth. You convert A to B, again convert B to A. Then multi-step, you are converting A to B, B to C, C to D. Many steps involved during the targeted molecule. There are million ways. Basically, organic conversion is the game here. More simply, what you should know. Naming reaction, it's a long list. Then regioselectivity, chemoselectivity, stereoselectivity, and diastereoselectivity, and stereospecificity, and simple stereochemistry, protection and deprotection, and rules. Example, Graham's rule, and reagent. It's also very long list. Then comparison between reagents and naming reagents and compound name. So many people ignore it. You should know the compound name. We will see what it is. If you don't know the basics, go and study separately. I'll just give outline of it, then we'll go into solving the problems. So better you learn all the basics before doing any organic conversion. So naming reaction, there are many. Here I try to give as much as possible. So from the basic aldol reaction to more interesting Chekhov reaction. So many are available. According to me, few are important, which is Bayer-Villiger oxidation, Beckmann rearrangement, Chekhov reaction, and enamine reaction. The list is going on. The list is longer. You can identify many more. Among that, Favorsky rearrangement, Hoffman rearrangement, and Michael addition, and Neff reaction. So there are the many. Here I try to give few. Then naming reaction, the final list. The important ones are Peterson olefination, Sharpless reaction, Suzuki coupling, Wagner-Merwin rearrangement, and Wittig reaction. Similarly, you can go on with reagent, but I suggest you should study all the catalysts, all the reagents, and all the naming reaction. This, if you want, take it as a snapshot. It will help you to understand the organic conversion much better. And the list continues. There are many. Of course, I might have avoided something. So you should choose your own reagent library, build on it, and do it for the organic conversion. Then we will see the next basics, comparing the reagents. Normally, the different reagents with the same compound behave differently. Here you have dimethylbenzene. Two different reagents you are using, bromine and light, bromine and acid. Bromine and light produce a radical. So radical mechanism follows. Radical don't attack the electron rich ring. So ring substitution don't happen. Only side chain substitution happen. On the contrary, aluminum chloride you are using it activates the ring. So ring substitution happen. Finally, you have ring substituted product. The concept you have to learn here is different reagents behave differently, give different products. Then compare the reactants. It is like reagent, but you have two different reactants, two different products. Same reagent you are using. Here I given E plus. E plus is electrophile. With toluene, ortho and para substitution will form because ortho and para will be electron richer. On the contrary, with nitrotoluene, only meta product is formed. It's aromatic electrophilic substitution reaction. This will help you to compare the reactant. Different set of reactant, different set of product. Then the regioselectivity. Here you have diene and dienophile situation. It's a Diels-Alder reaction. Dienophile can attack A ring or B ring or C ring. Where it will attack is the real question. It is called regioselectivity. Here B ring is weaker because of annihilation effect. A and C ring are individually aromatic. B will be considered as less aromatic. So B ring undergo Diels-Alder reaction. Even though all the rings are considered as same, only B ring reacts because of regioselectivity in Diels-Alder reaction. Then the next example, chemoselectivity. Basically, you are going to find which functional group reacts. Here you have meta-hydroxybenzoic acid. It's a phenol with acid in meta position reacting with sodium bicarbonate. Here two functional groups are there, alcohol and acid, which will react. Here acid is better electron donor, more acidic, so it reacts first. So only acid oxygen act as a nucleophile. Attack happened, you have the final product. Here if you look at it, among the two functional group, only one is react. It is called chemoselectivity. The concept you have to learn here is identifying which functional group reacts is called chemoselectivity. Then the stereoselectivity. Stereo means cis and trans, R and S. Many different concepts are there. For simplicity, I given cis and trans. Here, if you want to reduce butane with lithium and liquid ammonia, you have radical set mechanism. Radical anion form. Radical and anion of same charge trying to be away. So methyl group twisted, you have trans product. So even though you have the possibility of cis and trans, only trans is major to avoid the repulsion. So the concept you have to learn here is stereoselectivity means you are creating particular stereo product between the choices. Then the next basics, protection and deprotection. Suppose you have two functional groups. You want one functional group to react, other don't want to react. Here you play with kinetics. More reacting group will react fast. Here ketone is more reactive than ester, but you cannot conduct the reaction only in ester. So you mask the group of ketone by diol. Diol reacts, you have protection. Then lithium aluminum hydride reduce ester to alcohol. Then if we deproduct with the acid, you have ketone. So only one functional group you want reacts. The competition is prevented by the reactivity, basically by the chemical kinetics. Then the next basics, stereospecificity. Stereospecificity means the reacting species should be on perfect space. Here starting material is given. Basically you are doing HCl elimination. It's a E2 reaction. There are 3 hydrogen and 1 Cl, but only one hydrogen is anti to Cl. So A hydrogen and chlorine eliminates, you have E2 reaction. This is called stereospecificity. It needs specific stereochemistry to form the product. This is called stereospecificity in chemistry because among the other stereostructure, only one stereostructure is favored. Then very basic stereochemistry. There are many concepts are possible. Here a given basics. First is cis strands, then above the plane, below the plane, then axial, equatorial, then endo, exo, then syn, anti, then anomer, then epimer. These are all basic chemistry. Basically, we are studying the position of the functional group. It is also important. Then the rules in chemistry. There are many rules. Here I given few rules, which is Markovnikov, says up. More importantly, Cram's rule and Betts rule, Bayer's rule, or you can say theory, or Endo rule in Diels-Alder reaction. There are many available, but better you learn to master the organic conversion. Develop your own rule library to master the organic chemistry. Then the compound name. It's really an important one. Nobody will follow it. Suppose they given simply quinoline, you are reacting with lithium and liquid ammonia. What you will do? Even though you know chemistry, you know the reagent, you know the stereochemistry. If you don't know the quinoline structure, you are gone. So you cannot answer the question. So better learn and memorize the compound name. Then very common facts, which is very basic for the organic conversion. First one is low charge or no charge is stable. Always you quench the charges. Then cyclic product always form with less strain, which is very important. Then rate of intramolecular reaction is higher than intermolecular because no collision is required. Then mesomeric effect is greater than inductive. This is also very basic and important. And more important thing is less step is more. Always you do conversion with less number of steps because in paper everything is easy. In reality, even 3 steps makes the reaction very tougher. Yield will be low. So less step in conversion is always considered as more step. Then we are going into very important thing, which is solving the organic conversion. We are going to see 239 problem, very long list. Why so many? Because problems are best way to learn. It will give different perspective. It help you to analyze your memory and your conceptual ability and many more. So best way to learn anything is solve the problem. Let us see the first example. You have cyclobutane, side chain you have 2 methyl group, 1 chlorine. You are using methanol. You should find what will be the final product. Basically, the conversion is Wagner-Merwin rearrangement. It is all about cation stability. At first step, chlorine is the good leaving group. Chlorine eliminates, cation forms. Cation formed near the strainful 4-member ring. So strain should be relieved. 4-member ring become 5-member ring. So cation convert from side chain to main ring. It become 5-member cation. Then cation is a secondary cation. Chances of tertiary cation is there by methyl shift. So methyl shifted and you have hydrogen elimination. So you have the final product. The concept you outline here is you should master the all naming reaction and rearrangement to master the organic conversion. Then the second example, you have benzene with 2 methyl group with ortho relation. First set of reagent is bromine in aluminum chloride. Second set is bromine in lead. You should find which will be the major product. The reaction involves chemoselectivity. First, bromine and aluminum chloride. Aluminum chloride is the Lewis acid. It activates the ring. So ring substitution happens. On the contrary, bromine with lead form a radical. Radical cannot attack the benzene ring because of same charges. Only side chain reacts. You have alkyl bromide. Bromine and aluminum chloride gives aryl bromide. Bromine with lead gives alkyl bromide. Basically, the reaction is chemoselectivity. You can also consider it as regioselectivity. The concept we outline here is aluminum chloride promotes the ring substitution. Lead promotes side chain substitution. Then the next example, you have quinone. Second and sixth position, you have methyl group and you have bentadiene. You are heating it up. You should find what will be the final product. Here the problem in the blind side. It's a diene and dienophile reaction. Basically deals alder reaction. Here diene you should redraw with S form. Then you have dienophile. Diene and dienophile mean 4 plus 2 cycloaddition. So deals alder reaction. Since the addition is syn addition, methyl and hydrogens are syn to each other. You have the final product. The important concept in the conversion is you have to always imagine the reaction before you do organic conversion. Then the next example, you have cyclohexane, it is in the chair form. Methyl and bromine syn to each other, isopropyl trans to each other, all are in 1 to 4 position. You are using potassium hydroxide and heat. You should find what will be the final product. Here basically you are doing E2 elimination and you have the possibility of many hydrogen in the same position. This is the very interesting conversion because regioselectivity and regiospecificity in the same question. Here bromine is there, potassium hydroxide and heating it up. Basically E2 elimination. E2 elimination require anti-periplanar position. Here H and Br is the leaving group. So alkene will be formed. Here substitution is not possible because you are heating it up. So that will be minor product. Two possibility of hydrogen elimination A and B. B hydrogen elimination is major because it will form more substituted product which is says a product. So here regioselectivity comes, anti-periplanar positions. So B hydrogen eliminates, promote regioselectivity and stereospecificity. Both are in same form. The concept you have to learn here is you should master as much as possible fundamentals, then only you master the organic conversion. Then the next example, you have para-hydroxyaniso. You are using sodium hydroxide, epoxide with side chain chloride. You should find what will be the final product. Here you have benzene with two functional groups, ether and alcohol. You are using sodium hydroxide. Basically alcohol and sodium hydroxide, you form the salt which in turn form anion. There are two nucleophilicity. One is methoxide lone pair can act as a nucleophile and O- can act as a nucleophile. The charged nucleophiles are better, so O- dominates. Epoxide where it will attack, less hindered position is better. Even though it has A, B, C, three possibilities, only C is favored because of less hindered position. Then ring open. Epoxide can attack the leaving group carbon because carbon is the good leaving group. Again epoxide form. It's a marvel of organic chemistry, basics as well as combination of many factors. The concept you outlined here is charged nucleophiles are better. Epoxide reactions always involve in less hindered carbon. Then the next example, you have paramethoxytoluene. You are using acid chloride, aluminum chloride. You should find what will be the final product. Here aluminum chloride is there. Aluminum chloride can activate the ring, but acid chloride where it will form. It has two different positions. Ortho to methyl or ortho to methoxide is the major. Here ortho to methoxide is major. Here dominant electronic factor is mesomeric because electron donation of mesomeric is full electron donation. Inductive effect is a partial electron donor. So mesomeric effect is stronger. So acetyl group form ortho to methoxy group. The concept you outline here is mesomeric effects are stronger than inductive effect. Then the next example, you have naphthalene. It's a fused amide and beta position methyl groups. You are using bromine and ferric chloride. You should find where the substitution will happen. Here if you look at it, substitution can happen at A and B. So attacking species is electrophile. So bromine can attack only electron richer ring. Carbonyl is the electron withdrawing group, so it will weaken the ring, and amine is the electron donating group. It will increase the electron density. So attack on A is major, attack on B is minor. The concept to outline here is in electrophilic aromatic substitution reaction, electron density decides the final product. Then the next example, you have naphthalene. It is attached with O-style group. You are reacting with aluminum chloride and water. You should find what will be the final product. By looking at the plain side, it is nothing, but technically it's a Fry's rearrangement movement of first-style group. Basically, you have two different positions, alpha and beta in the same ring. Alpha position is favorable for the transfer. As it attacks, you have cation formation. Then the acyl cation leaves. It attacks in the alpha position. The kinetic product is favorable under the present condition. It is also like aromatic electrophilic substitution reaction. The concept we outlined here is Fry's rearrangement can occur in the naphthalene system. Then the next example, you have decline, 2-methyl group, hydroxy and amine. You are using sodium nitrate and HCl. You have to guess what will be the final product. Here problem can be solved easily if you draw in the chair form. Hydroxy and amine are trans to each other. You are using NaNO2. It is like diacetization. N2 plus form as a salt. It is a good leaving group. So O minus attacks. You have epoxide formation. If you redraw nicely, you have below the plane epoxide with final product. The concept you outline here is you should master the stereochemistry and conformation to achieve the best possible conversion reaction. Then the next example, you have cyclopentane. Methyl and acetyl groups are near to each other. You are using sodium borohydrate and acidic hydrolysis. You should find what will be the final product. Here reducing agent you are using, which is sodium borohydrate, which will selectively reduce the carbonate. You have alcohol. Then you are using acidic condition. Acidic condition converts alcohol into water. It's a good leaving group. So you have cation formation. So cation near the strainful 5-member ring. So Wagner-Merwin rearrangement is possible. So ring expands. 5-member ring becomes 6-member ring. Cation switched from the side chain to ring, cation near the methyl group. Then cation has to be quenched, so H eliminates, you have alkene formation. But in alkene formation, more substituted alkene is stable according to the Sesop rule. So more alkene is formed, you have the final product. The concept you outline here is whenever you have cation in the strainful system, the strain always released. Then the next example, you have metadichlorobenzene and you have carbonyl which is with chloride and methylene chloride at the another end, 2 chlorine with different attachment. You are using aluminum chloride. You should find what will be the final product. Here Lewis acid you are using. Lewis acid will remove the chlorine from the carbonyl, not from alkyl chlorine. So ring substitution is possible. So among the 2 chlorine, only 1 chlorine will be eliminated from acyl cation, which is 1 chemoselectivity. And acyl cation, where it will attack is the real question. Chlorine is mesomeric in nature. It only provides ortho and para for the incoming group. So among the 3 possibilities, PQR, R will be the best possibility because acyl group is para to A chlorine, ortho to B chlorine. It obeys our concept perfectly. Others are against our concept. So only product is R product, which is major. The concept you outline here is regioselectivity and chemoselectivity. It's a critical part of organic conversion. You should master it. Then the next example, you have linear chain with bromine and acid. Bromine is stereochemically specified. You are using sodium hydroxide. You should find what will be the final product. Here bromine is there, you are using base. Base is the strong nucleophile. So what it will do is it will attack the bromine, form a SN2 mechanism product which is inversion in configuration. Let us analyze other possibility PQR. P is major, Q is minor because OH is the strong nucleophile. It don't form immediate cation. Moreover, cation formed near the acidic group, which is electron withdrawing group, is unstable. So it is not possible. R is minor because heating only promote elimination reaction. So R will not be the possible product. So only possible product is P, which is major, SN2 mechanism, inverted one, and definitely it's a major product. The concept you outline here is you should master all basic mechanism to master the organic conversion. Then the next example, you have conjugated ketone which is cyclohexanone. You are reacting with methyl magnesium halide in acidic condition, methyl magnesium halide with copper chloride in acidic condition. Only difference is copper chloride. You should find what difference it can make in the final product. Here methyl magnesium chloride we are using, it's a hard nucleophile. So it attacks the second position in the cyclohexanone. So it attacks, you have O minus, then it is quenched with hydrogen. So basically it's a 1,2 addition. Normally hard nucleophile undergo that. But interesting fact comes whenever you have copper chloride. Copper chloride will undergo 1,4 addition, or you can say Michael addition reaction. So copper attacks, charge travels because oxygen can stabilize the negative charge because of electronegativity. Then as it attacks, you have enol. Enol can be tautomerized to ketone. The addition is 1,4 addition. Product is ketone there. The concept you outline here is soft nucleophile undergo 1,4 addition, which is also called as Michael addition. Then the next example, you have benzene. 1,2 position you have bromine. 4th position you have nitro group. You are reacting with sodium methoxide. You should find what will be the final product. Here sodium methoxide you are using. Possibilities are many. Here are given two basic and fundamental pathway P and Q. In both cases, attack on bromine is feasible because bromine is the good leaving group. So there is two bromine, two possibility P and Q. P attack leads to the anion. Anion travels to the nitro group. Nitro group is electron withdrawing in nature, so it stabilizes the anion. It could be the major product. On the contrary, if you look at the Q, attack on the second bromine, the anion travels which is away from nitro group. It cannot have extra stability. Basically, the mechanism is addition elimination mechanism. If you are interested, go and study separately because it's a nucleophilic addition in the benzene. Here P product is definitely major because of extra stability of the anion. The concept you outline here is in aromatic nucleophilic substitution reaction, stability of anion dictate the final product. Then the next example, you have cyclopentane. Side chain you have alcohol with 2 methyl group. You are reacting with sulfuric acid. You should find what will be the final product. Here you have alcohol, acid you are using, which will remove OH as the water. You have the cation. Cation near the strainful ring because 5-member ring is against the tetrahedral carbon bond angle. So strain is high. It should reduce the strain. It reduces it by ring expansion. So ring expand. cation moved from 6th carbon to 1st carbon. If you redraw nicely, you having 5 member to 6 member transformation. So cation is there, it has to be quenched. It will be quenched with major substituted product. It will be quenched by alkene formation with more substituted product. The concept you have to learn here is, in Wagner-Merwin rearrangement, if there is no proper quenching pathway, more substituted alkene will form. Then the next example, you have cyclohexane, chlorine, deuterium and methyl hydrogens are specified. Chlorine and deuterium trans to each other. Chlorine and methyl also trans to each other. Methyl and deuterium is cis to each other. You are using alcoholic KOH. You should find what will be the major product. You can solve the problem better if you redraw the molecule to the chair form, because you can see the bond angle there. So if you redraw nicely, chlorine and deuteriums are trans to each other. Since you are using the strong base, anti-periplanar elimination with E2 mechanism happen. Here many hydrogen, here 3 hydrogen, 1 deuterium is there. Only deuterium is trans to the chlorine. It eliminates, you have the alkene. Other hydrogens are syn to chlorine, so all will be the minor product. So major product will be anti-periplanar relationship with chlorine and deuterium. The concept you have to learn here is, E2 mechanism demands anti-periplanar position. Then the next example, you have chlorobenzene. You are converting into salicylaldehyde. You should find reagents and number of steps involved in the transformation. The transformation will be simple if you know the two naming reaction. One is Dow's process, another is Reamer-Tiemann reaction. Dow's process converts chlorobenzene into phenol. Strong heating with higher condition leads to the phenol. Then you have CHO addition, which is by formaldehyde NOH from Reimer-Tiemann reaction. So two functional group added from the starting material. One is OH, another is CHO. Here Dow's process gained the name because you are substituting chlorine with alcohol. That's why the naming reactions are important here. The concept you have to learn here is, you should memorize all the naming reaction to master the organic chemistry. Then the next example, you have para-hydroxybenzoic acid. You are using base and methyl iodide. You should find what will be the final product. Here you have acid and alcohol, both can be a nucleophile, but alcohol is the better nucleophile because the charge don't involve in the resonance. In COO- charge is involved in the resonance, so charge density become half there. In the case of O-, charge is on single atom, charge is more denser. More density will be the good nucleophilicity. So O- will be the nucleophile, not COO-. So O- attacks, you have new OC bond, you have the final product. The concept you have to learn here is, to find the nucleophilicity, you should find the electron density. Then the next example, you have benzene. Side chain you have alkyne. Alkene with cis fashion. You are using hydrogen, palladium, calcium carbonate and quinoline. You should find what will be the final product. Here the reaction may look simple, but it has many possibilities. PQRST. Only P is major product if you know the Lindlar's catalyst mechanism. Because palladium only selectively reduces the alkyne, not alkene. It's a chemoselectivity and it is also stereoselective. It converts alkyne into cis form, not the trans form. So it is a wonderful organic conversion reaction. It is all about basics. Other products are, you have benzene reduction as well as side chain reduction, only alkene reduction, only alkyne reduction. all possibilities, but only P is major there. The concept you outlined here is the role of reagents and the reagent impact on the starting metal is important. Always memorize the reagents. Now the next example, you have halide bromide. It's a 3-carbon system. You're reacting with potassium hydroxide, tertiary butoxide. You should find what will be the final product. Here same reactant, two different reagents, KOH and potassium tertiary butoxide. But it can make a large difference. OH minus can act as a nucleophile, but tertiary butoxide cannot act as a nucleophile. But it can act as a base, it abstracts the proton, elimination dominates. On the contrary, potassium hydroxide involved in the substitution reaction, not the elimination. Pr become OH there. So bulky nucleophile followed E2 mechanism. Strong nucleophile follow SN2 mechanism. This is the best example comparing the reagents. The concept you have to learn here is bulk bases only act as a strong base, not as a nucleophile. Then the next example, you have cyclohexane, bromine and methoxide in the trans form. You are reacting with sodium hydroxide, water. You should find what will be the final product. Here the problem can be easily understood by drawing with flat structure. Here you have internal nucleophile OCH3 and good leaving group bromine. So epoxide will form. So epoxide kind of intermediate form which is cation. Then OH attacks. You have OH at the same position. Why this problem is interesting means leaving group and the incoming group in the same plane which is above the plane. Normally what you would expect is SN2 reaction with inversion of configuration. Since the neighboring group participation is there, retention of configuration happen. The concept you have to learn here is neighboring group participation is the strong factor. It will dominate even simple SN2 reaction. Then the next example, you have cyclobutane. Side chain you have 2 methyl group and bromine. You are using ethyl alcohol. You should find what will be the final product. Here you have bromine which is in the tertiary carbon. So SN1 mechanism is possible. Bromine is the good leaving group. It leaves cation form. Cation form near the strainful 4-member ring. The ring is strainful because it is away from tetrahedral carbon bond angle. So it is strainful. Since cation is near to cyclobutane, it tried to expand itself and minimize the strain. So 4-member ring will become 5-member ring by reducing the strain. Then the cation switched, but it converts into tertiary into secondary. Here cation stability is reduced, but ring strain reduction is critical, so it happened. Then ethanol attacks, you have final product. The concept you have to learn here is whenever you have competing factor, you should know the priority. Here ring strain reduction is high priority than the stability of the cation. Then cyclohexyl bromide, you are converting into linear compound with 2 aldehyde and 1 fluorine. You should find number of steps and reagents involved in the organic conversion. You start from basic alcoholic KOH because you have to create the carbonyl. How you can create it? From alkene to ozonolysis. So to form alkene, you are using alcoholic KOH. HBr eliminates, alkene forms. Here alpha halogenation is required because you have to substitute the fluorine. So first we substitute with N-bromosuccinimide. It's a very important reagent. It's regioselective. It only attacks the alpha carbon. So alpha bromination happens. Then if you use silver fluoride, bromine converts into fluorine. If you do further VOS analysis, you end up with required product. The concept you outline here is we should master the reagents for effective organic conversion reaction. Then the next example, you have benzene with acid and benzyl group attached to it. You are reacting with SOCl2, aluminum chloride, zinc amalgam and HCl. You should find what will be the final product. Here the problem given with the hidden structure, you have to redraw the molecule. The benzene is there. If you redraw the benzene, you have used benzene with methylene and acid is there. You are using acid chloride. You are using SOCl2. SOCl2 converts acid to acid chloride, functional group conversion. Then you are using aluminum chloride. It's an intramolecular Friedel-Crafts reaction. It happened with 6-member ring. It's a perfect position. Carbon bond angle also allow it. So only ortho substitution happened, not the para. It's a regioselective reaction. Then next step you are using zinc amalgam and HCl. It will reduce selectively carbonyl group, not the benzene. It's a chemoselectivity. So you play with all the reagent, end up with completely fused cyclic product. The concept you outline here is naming reactions are mandatory for completing any organic conversion reaction. Then the next example, you have chlorobromobenzene which is with meta relation. You are using magnesium and ether and acetaldehyde. You should find what will be the final product. First step, you are using magnesium. Magnesium form Regnard reagent. Here the interesting question is whether bromine or chlorine form in. Bromine form dominantly. So magnesium form Regnard reagent with bromine. Then it behave like nucleophile because it generates carbon ion. It attacks the aldehyde. You have final alcohol. The concept you outline here is Regnard reagent selectivities are iodine is higher, then bromine, then chlorine, then fluorine. Then the next example, you have chlorobenzene. You are reacting with butyl lithium and anthracene. You should find what will be the final product. Here butyl lithium you are using, it's a strong base. It abstracts the proton which form benzene. It's a benzene with one triple bond. It can act as a dienophile. So diene and dienophile situation. So it can be a Diels-Alder reaction. But where the reaction occurs is a real question. A, B, C ring. Only B ring involves there. Because B ring contains less aromatic, it can act as a diene. You end up with final product. The concept you outline here is in anthracene middle ring is weak. It will undergo Diels-Alder reaction. Then the next example, you have benzene attached with cyclohexane and methyl group. You are reacting with N-bromosuccinamide. You should find what will be the final product. The reaction is simple, all about radical stability. There are 4 possible products A, B, C, but C is major, all because of radical stability. A product is not possible because you are not activate the ring with any Lewis acid such as ferric chloride or aluminum chloride. So A is minor. B is minor because of secondary radical. C is major, it is tertiary as well as benzyl. So it's highly stable and highly probable. Finally bromine attacks, you have the final product. The concept you outline here is whenever you have intermediate, always analyze the stability and predict the final product. Then the next example, you have chlorobenzene reacting with butyl lithium and cyclopentadienone. Further heating it up, you should find what will be the final product. Here strong base you are using, it abstract the proton, it form benzene. Benzene means benzene with triple bond. It can act as a dienophile. So diene and dienophile situation mean 4 plus 2 cycloaddition. It's a Diels Alder reaction. So 4 plus 2 cycloaddition happen. You have bridged carbonyl. If you are heating mean CO will leave us a gas. Why? Because ring strain promote it and most stable aromatic naphthalene forms. It's a wonderful conversion reaction, all about stability. The concept you outline here is aromaticity is the stabilizing factor. It dictates the final product. Then the next example, you have cyclopentane. It's a carbonyl with alpha position methyl group. You are using LDA and heating it up. Further, you are reacting with dihalide with alkene. You should find what will be the final product. The reaction is wonderful, involves many selectivity. First thing will be LDA. LDA is the strong base. It can abstract the proton, but it is bulky, only abstract, less steric position or less hindered position. So anion form which can act as a nucleophile. Since the temperature is high, kinetic product is favored, so anion form. But anion where it can attack, which bromide, whether it is sp3 carbon containing bromide or sp2 carbon containing bromide. sp3 carbon bromide contain very good leaving group ability because of sp3 carbon new CC bond formed. This reaction may look with big structure and big reagent but involves simple chemistry. The concept you outline here is leaving group in sp3 carbon is effective, then sp2 carbon. Then the next example, you have acetophenone with peracid. You should find what will be the final product. By looking at the ketone and peracid, you might realize it's a Baeyer-Villiger oxidation or Baeyer-Villiger rearrangement. First step will be attack of nucleophile to the carbonyl. New CO bond forms. Carbon with many heteroatom is unstable, so migration happen. You have cation near the alcohol. So cation forms, rearrangement occur. Cation near the alcohol quenched as carbonyl. If you redraw nicely, migrated group become a ester substituted. Here migrating ability of phenyl is higher than methyl because of intermediate less electron density. You can say intermediate is cation. The concept you outline here is in Baeyer-Villiger oxidation, electron rich group migrates because of electron deficient intermediate. Then the next example, you have cyclopentane with diol group with diphenyl. You are reacting with sulfuric acid. The compound contains vicinal alcohol. You are using sulfuric acid. You should find what will be the final product. By looking at the diol and acid, you might realize it's a phenol-phenaclone rearrangement. Basically a cation forming rearranged product. Here two cation can form, which is cation near the ring, cation near the phenyl. Cation near the phenyl is stable because of stability from phenyl group. So cation formed. Cation near the strainful 5-member ring. So ring tried to open itself. 5-member becomes 6-member. During the transformation, cation formed near the alcohol. Alcohol release the hydrogen, quenched as ketone there. You start from a linear structure, end up with completely cyclic structure. The reaction is assisted by strain and cation stability. The concept you outline here is whenever you have intermediate, always strain will be relieved from the system. Then the next example, you have cyclopentadiene with methyl group reacting with nitroalkene, heating it up using base and using titanium trichloride. We should find what will be the final product. Here diene and dienophile situation. So 4 plus 2 cycloaddition is possible. Heat also supporting the reaction. 4 plus 2 cycloaddition happened. Here one very important rule is endo rule. Always endo product form in the bicyclic system during the Diels-Alder reaction. So endo is the major product. Then you are using NaOH and titanium trichloride. It's a NEF reaction. Basically a functional group conversion reaction converts NO2 into CO. The concept you outline here is all conversion deeply involve naming reaction. Here it's a Diels-Alder reaction and NEF reaction. Then the next example, you have decline, side chain you have oxime and methyl group. You are using sulfuric acid. You should find what will be the final product. By looking at the oxime and acidic condition, you might realize it's a Beckmann rearrangement. First step of the reaction will be OH elimination as the water, then methyl group migration. Both happen at the same step. For convenient, we shown as the individual steps. Methyl moved mean cation forms, then water attack. In water, OH minus is the nucleophile. It attacks, then tautomerism happen. You have ketone there. You end up with amine because ketone near the amine is called amine. Finally, you have rearranged product. In starting metal, methyl group or tecline carbon migrate, but tecline carbon is a rigid carbon. Due to the steric reason, it cannot migrate. The concept you outline here is in Beckmann rearrangement, always trans group migrate due to the steric reason. Here cis group migrated. Then the next example, you have cyclohexanone, alpha position you have alkane. You are reacting with alpha, beta and saturated ketone and butyl lithium. We should find what will be the final product. Here butyl lithium you are using. Butyl lithium is the strong base. It abstracts the proton. It becomes nucleophile. Nucleophile is carbon based. Carbon nucleophiles are soft. It will undergo 1,4 addition with alpha, beta and saturated ketone. C- attacks. You have new CC bond. Then the compound has alpha hydrogen. So proton abstraction is again possible, which leads to the intra-aldol condensation. The condensation creates new CC bond, tecline architecture form. Finally, you have water elimination because conjugated ketone is more stable than non-conjugated. Finally, you have decline with conjugated ketone. The concept you outline here is carbon nucleophiles are soft. It will undergo 1,4 addition. Then the next example, you have decline, above the plane epoxide, below the plane 2 methyl group in 1,2 position. You are using acid and hydrolysis. You should find what will be the final product. The problem can be easily solved if you redraw in the chair form. So you redraw the decline with chair form. Epoxide above the plane, methyl group below the plane. Then you are using the acid. Acid attacks the epoxide oxygen. Ring opening will be there. In next step, OH minus attack. Ring open in the transposition to avoid the steric effect. So you have diol with transposition. The concept you outline here is you always simplify the structure to master the stereochemistry. Then the next example, you have epoxide with phenyl group reacting with tin chloride and methanol. You should find what will be the final product. Here tin chloride is the Lewis acid. You can imagine it like H+. So it attacks the epoxide. Ring can open either way, but phenyl can stabilize the cation better. So only A break is possible. B break is minor because it forms primary cation. Phenyl can stabilize much better. So phenyl cation forms, then methoxide attacks. You have the final product. This reaction driven by two factors, cation stability as well as ring strain. The concept you outline here is acid catalyze epoxy ring opening reaction controlled by the cation stability. Then the next example, you have cyclohexanone. LDA you are using benzaldehyde as a reactant. You should find what will be the final product. Here you are using the LDA. LDA is a lithium diisopropylamide. It's a base. It abstracts the proton. You have nucleophile. Nucleophile can undergo condensation reaction with aldehyde. It cannot self-condense because aldehyde is more reactive than ketone. So benzaldehyde reacts first rather than self-condensation. So it will be the major product. So nucleophile attacks the carbonate. New CC bond with alcohol. Then water elimination leads to the conjugated, more stable ketone. The driving force is conjugation. You are creating continuous conjugation. The concept you outline here is aldehyde reactivity is higher than ketone. It will capture the nucleophile quickly. Then the next example, you have cyclohexanone with cyclobutane at the alpha position. It is an spiro compound reacting with HCl. You should find what will be the final product. Here Wagner-Merwin rearrangement possibility is there. First step, H plus attacks the carbonyl. You have alcohol with cation. It's a secondary cation. Moreover, strain full 4-member ring is there. So ring open, secondary cation become tertiary cation. Because stability of tertiary cation is high as well as ring strain is relieved. Ring is going from 4-member to 5-member. So this step is possible. Then cation has to be quenched. So carbon migrate. You have cation near the alcohol. If you read rather nicely, spiro compound with cation near the alcohol. Alcohol quenched as carbonate. With H plus elimination, you have the final product. The concept you outline here is whenever the intermediate form, ring try to relieve itself to the larger rings. Then the next example, you have cyclopentane with alcohol and methylamine. You are reacting with sodium nitrate and HCl. You should find what will be the final product. Here you have amine with sodium nitrate and HCl diacetization reaction. NH2 become N2 plus. It's a salt. It can easily leave as a N2 group, form cation, but cation near the cyclopentane ring. So it try to open itself, relieve the strain. So 5-member ring becomes 6-member. You have cation near the alcohol. Alcohol quenched as carbonyl. The elimination of H plus. The concept you outline here is like benzene system, linear system also can form diazonium salt. It can readily form cation involved in Wagner-Merwin rearrangement. Then the next example, you have the oxime. One side you have phenyl, another side you have methyl. Alcohol also there. You are using the sulfuric acid. You should find what will be the final product. Here oxime in acidic condition. Definitely you should understand that it's a Beckmann rearrangement. First step will be OH removal. OH removal will be assisted by the migration. Since the intermediate is the cation-like species, it's electron deficient. So electron rich group migrates. You have cation at the carbon. Then OH group attacks, it form enol-like compound. Then tautomerism occur, you have amide there. The concept you outline here is in Beckmann rearrangement, always trans group migrate. Then the next example, you have butane, you have sodium and ammonia. Second step, you are using bromine and CCl4. You should find final product is optically active or not. Here sodium and ammonia you are using, it forms set-base radical reduction mechanism. So it form always trans product. It's a stereoselectivity, only trans product is formed. Then bromine addition. Bromine addition also a anti-addition. It leads to the completely anti-product. Anti-product means bromine anti-periplanar to bromine, methyl anti-periplanar to methyl, hydrogen anti-periplanar to hydrogen. It is a meso compound. Definitely it's not optically active because inside plane is there. So it completely optically inactive compound. The concept you have to learn here is sodium ammonia reduction is stereoselective trans reduction. Bromine addition is anti-addition. Then the next example, you have cyclohexanone. Side chain you have 4 methylene group and azide reacting with titanium trichloride. You should find what will be the final product. The reaction is the Smith reaction. Azide in the Lewis acid condition means it's a Smith reaction. First step will be the attack of amine to the carbonate because N2 is the good leaving group. Amine has lone pair. It can act as a nucleophile. It attacks, you have intramolecular Smith reaction. It attacks, it forms the alcohol. Then if you read down nicely, you can see 6 to 7 member ring transition. Then the water elimination. After the water elimination, you have N2 group. It has to be quenched. So what really happens is carbon migrate, N2 elimination, cation form near the alkene there. Then OH attacks. OH attached with alkene means it's like enol. Tautomerism happened. You have amide there. So starting from azide, end with amide, it is called Smith reaction. The concept you have to learn here is with functional group and reagent, you can categorize the naming reaction. Then the next example, you have linear compound with one position you have alkene, another position you have conjugated alkene with methyl group. You are heating to high temperature 180 degrees Celsius. You should find what will be the final product. Here the problem in the blind side. You have the diene in the system, dienophile at the end. Chances of Diels-Alder reaction. You can imagine it better when you redraw nicely. You bring diene and dienophile closer. 4 plus 2 cycloaddition happen. You have final cyclic product. The concept you have to learn here is you should always imagine the reaction and its possibilities. Then the next example, you have cyclohexadiene reacting with phosphorus halide and heating it up, and lithium salt of dimethylamine and formaldehyde. Here 3 different reagents. You should find what will be the final product. Initial step you have diene. In halide you have alkene. Alkene with cationic phosphorus act like a dienophile. So it's a diene-dienophile situation. Diels-Alder reaction is possible. 4 plus 2 cycloaddition happen. You start from planar compound to bicyclic compound with alkene. Then you have phosphorus cation. Lithium salt of amine you are using. It's a strong base. It forms halide. So to promote the halide, you are using the strong base. Then formaldehyde reacts. You have alkene formation. So it's a functional group conversion reaction. You are converting carbonyl group into alkene by the use of halide. It is called Wittig olefination reaction. The concept you have to learn here is, as you see, naming reactions are very important. Without that, you cannot identify any meaningful product. Then the next example, pyrrole you are having. Second position you have oxime attached with methyl group. You are using sulfuric acid. You should find what will be the final product. Here you are having oxime in acidic condition. So possibility of Beckmann rearrangement. First step OH removal with water. But migration of trans group happened because in Beckmann rearrangement it's very stereospecific. Only trans group migrates, water eliminates. You have cation near the alkene, then cation quenched with OH minus. After the attack, you form enol. That enol can be converted into ketone through tautomerism. So the concept you have to learn here is in Beckmann rearrangement, irrespective of the functional group, only trans group migrates. Then the next example, you have alkene, both position you have cyclopentane, you are using hydrogen peroxide and sulfuric acid. You should find what will be the final product. Here alkene you are having, you are using hydrogen peroxide, it forms diol. Whenever you have 1,2-diol in acidic condition, phenol-phenolone rearrangement is possible. So first step will be the water removal. H plus attack OH, it removed as the water there, but it can be assisted by the ring opening because 5-member ring is very strainful. Ring open, 5-member ring becomes 6-member ring. The compound also becomes pyro compound. Cation also switches to alcohol. If you redraw nicely, you have cation near the alcohol. It is quenched as carbonyl. You have the final product. The concept you have to learn here is in phenol-phenolone rearrangement, cation is the intermediate. Ring will be open if there is strain in the system. Then the next example, you have cyclobutane, side chain you have alcohol and 2-methyl group. You are reacting with sulfuric acid. You should find what will be the final product. Here alcohol is there, acidic condition, definitely cation formation. So the possibility of Wagner-Mervin rearrangement, alcohol removes the water, form cation. So strainful 4-member ring near the cation mean ring will open, cation switches. From the side chain, cation move to the ring system. If you read nicely, you have the cation there. Then again the same alcohol in acidic condition. As it attacks cation form, this time methyl group migrates to form the stable tertiary cation. So finally end up with alkene for the quenching of cation. Basically the reaction continues until the stable alkene is formed. The concept you have to learn here is always finalize the product with the all utilization of functional group. Then the next example, you have ketone with 2-side phenyl group. You are using the peracid. You should find what will be the final product. Here you have ketone, you are using the peracid mean. It's a Baeyer-Villiger oxidation rearrangement reaction. First step will be attack of nucleophile to the carbon. It's a nucleophilic addition reaction. You have alcohol or unstable peroxide bond. So what really happened? Phenyl migrates, peroxide leaves. You have cation near the alcohol. Cation near the alcohol quenched as the carbonyl. You end up with ester there. If you redraw nicely, you can identify the final product clearly. The concept you have to learn here is in peracid, acetate anion is the good leaving group. RCOO minus is the good leaving group which promote the Baeyer-Villiger rearrangement. Then the next example, you have cyclohexanone reacting with hydroxylamine and sulfuric acid. You should find what will be the final product. Here you have ketone, you are using hydroxylamine, so the oxime formation. Oxime in acidic condition promote the Beckmann rearrangement reaction. First step will be OH remove as a water. It will be assisted by trans group migration. Trans group is the ring carbon. So ring carbon attacks, ring expansion happen. You have cation near the alkene. If you redraw nicely, 6-member ring becomes 7-member ring. Then OH attacks, you have enol-like architecture. Then the tautomerism happened. You end up with finally amide there. The concept you have to learn here is, in Beckmann rearrangement, always trans group migrate. Then the next example, you have cyclopropane. Side chain you have chloride reacting with HCl. You should find what will be the final product. This reaction is extremely interesting because Wagner-Merwin possibility is avoided. In this reaction, first step will be the chlorine removal. You have cation formation. You might expect strainful 3-member ring will open to 4-member, but it is not possible. Why? Because cyclopropyl cation itself stabilized cation because of perpendicular p orbitals. P orbital provides conjugation or resonance better. You have cation stabilization. The stability is good, so ring don't expand. Final product is expected alcohol. The concept you outline here is, in cyclopropyl system, ring don't expand because of extra stability of cyclopropyl cation. Then the next example, you have cyclohexanone reacting with titanium tetrachloride, zinc copper coupled, potassium permanganate and sulfuric acid. You should find what will be the final product. Here carbonyl is there, titanium tetrachloride and zinc copper couple you are using. So it's a McMurray coupling reaction. You are converting carbonyl into fused alkene there. Starting metal coupled through alkene there. Then you are using the permanganate. Permanganate converts alkene into diol there. Diol in acidic condition means pinacol-pinaclone rearrangement. First step will be the water removal. OH converted into water by addition of H+, but it has assistance from the ring opening. 6-member ring becomes 7-member, ring open, cation form near the alcohol. If you redraw nicely, you have spiro compound with 7 and 6-member ring and cation near the alcohol. H+ eliminate, cation quenched as ketone there. The concept you outline here is, rearrangement and naming reactions are backbone of organic conversion reaction. Then the next example, you have benzene with acid and amine reacting with nitrous acid, sodamide and ammonia. You should find what will be the final product. Here amine is there, you are using the nitrous acid. It converts amine into N2+. Here N2+ and COO- is there. Both are very good leaving group, CO2 and N2. It form benzene. Benzene means benzene with one triple bond. Then sodamide you are using, end up with aniline. The concept you have to learn here is, two leaving group near in the benzene mean you end up with benzene. Then the next example, you have toluene with second position, you have cyanide. You are using nitric acid and sulfuric acid. You should find what will be the final product. Here sulfuric acid and nitric acid you are using. It's a nitration reaction. Aromatic electrophilic substitution reaction. Electrophile is NO2+, where it will attack. Basically, which group control is the question, cyanide or methyl. Here major position will be the fourth position because it is perfect for methyl and cyanide, because methyl is the ortho para donor, cyanide is the meta donor. Cyanide is electron negative, direct to the meta position. Methyl is electron donating, which direct to ortho para position. So A product will be major. B also equally possible because of steric effect. Possible solution will be A product. The concept you have to learn here is whenever you have competing functional group, choose the middle path, identify the major product. Then the next example, you have cyclohexadiene with two exocyclic double bond. You are reacting with vinyl chloride at high temperature. You should find what will be the final product. Here if you look at it, you have diene and dienophile situation, but problem is two diene A and B, which diene will react. Here stability of product is very much important. It can be created in multiple ways. Here A alkene reacts mean you have major product because aromaticity is created more stable. On the contrary, B alkene react mean you have highly strained bicyclic compound. Why it is strained mean sp2 carbon in the 4-member ring. sp2 carbon require 120 degree. Here only 90 degree. Highly unstable, highly strainful. The concept you have to learn here is whenever the chances of aromaticity, product always move to aromaticity because of its higher stability. Then the next example, you have linear chain compound with one bromine, one chlorine, one methyl group. You are reacting with sodium and ether, then bromine heating it up, finally with alcoholic KOH. You should find what will be the final product. Here sodium you are using, you have dihalogen mean Woods reaction. So ring try to close. If you redraw nicely, you have 6-member ring. It is a less strainful, favorable product. That's why Wood reaction also possible. Moreover, it forms cyclic product. Here 6-member ring with one side chain methyl. You are reacting with bromine and heating it up. So bromine substitution happen. Then you are using alcoholic KOH. Two reactions are possible. One is more substituted alkene, less substituted alkene. More substituted alkene is formed, that is the major product. The concept you have to learn here is you have to master the reactions and various kind of rules to master the organic conversion. Then the next example, you have cyclohexene. You are reacting with N-bromosuccinamide and water and sodium hydride. You should find what will be the final product. Here if we redraw to the chair form, problem can be easily understood. So we redraw to the chair form. N-bromosuccinamide reacting with alkene forms brominium ion. It is like epoxide. Water attacks. It's a SN2 reaction. So backside attack is important. What really happened? Bromine and hydroxide form trans to each other. The interesting fact is further you are using sodium hydride. Sodium hydride remove the proton from the system. You have O nucleophile and bromine is a good leaving group. It form epoxide. If you read it nicely, you have epoxide in the cyclohexane. This reaction is wonderful because you are starting from brominium ion, end with epoxide. Then the next example, you have naphthol and quinoline reacting with same reagent, lithium and liquid ammonia. You should find what will be the final product. If you are using lithium and liquid ammonia, it's a Bitch reduction reaction. But interesting fact is what difference it can make. In naphthol, oxygen is the electron richer system. Since attacking species is electron, attack happen on A ring. On the contrary, quinoline nitrogen ring is electron deficient, so attack happen on D ring. One case happen on the substitution, another case attack happen in the benzene ring. Basically, electron density decide which attack will happen. You have 1,4 reduction there. The concept you have to learn here is in Bitch reduction, always less electron deficient ring get reduced. Then the next example, you have ketone, side chain you have bromine, you are reacting with sodium hydroxide. You should find what will be the final product. Here you may think that bromine to alcohol formation is simple one, but it is not the case. First step will be abstraction of proton, because proton abstraction leads to the anion. It can be stabilized by carbonyl. So E1CP mechanism is possible because of sp2 carbon. Then the anion is there, it has to be quenched. What really happened? Anion quenched with good leaving group form alkene. You may think of intermolecular reaction, but intra is favored because it don't require any collision. Because conjugated ketone is the major product. The concept you outline here is whenever you have alpha stabilization, proton removal leads to E1CP mechanism. Then the next example. Here you have oxime with methyl and toluene group reacting with sulfuric acid. You should find what will be the final product. Here oxime is there, acidic condition means Bachmann rearrangement reaction. It's a stereospecific reaction. Only trans group or anti group migrate. Here toluene is anti to OH. Proton attacks leads to the H2O plus formation. It's a good leaving group. Trans group migrates, you have carbocation. Then OH minus attack, which is from water. You have enol-like product. Then tautomerism occur, you have amide. You are starting from oxime, end with amide. The concept you outline here is in Bachmann rearrangement, anti-trans group migrates. Then the next example, you have piperidine, second position you have methyl group. You are reacting with excess methyl iodide. Further you are adding silver oxide and heating it up. You should find what will be the final product. The reagents may look simple, but it involves continuous Hofmann elimination. First step will be methyl iodide attack on amine. It will form quaternary amine. Here Hofmann elimination is possible. What really happened? It formed alkene there by ring opening reaction. Ring open. Again you have quaternary amine. Here major product will be the less substituted product. Even though A and B hydrogen is there, B hydrogen elimination is major. You have alkene and amine. Again methyl iodide attack. The reaction repeats. You have quaternary amine elimination. You end up with diene there. The concept you have to learn here is until the amine group is available, Hofmann elimination occurs, less substituted product will form. Then the next example, you have epoxide, side chain you have chlorine, you are using sodium methoxide. You should find what will be the final product. Here multiple reaction possibilities there. It's a regioselective reaction. Sodium methoxide can attack chlorine, epoxide A and B pathway. So totally 3 different pathways A, B, C. Here attack on C will be minor because you have strainful epoxide is there. So only A and B attack is possible. Since the SN2 mechanism is dominant, you have steric attack is major. So attack on A on major, you have ring opening with O minus. The anion can be the nucleophile. Chlorine also a good leaving group. So internal substitution reaction happen. You have chlorine elimination. Epoxide formed again. Starting material and products look like similar but completely rearranged product. The concept you outline here is SN2 reaction occur in epoxide. Always steric attack will be happen. Then the next example, you have isobutene reacting with HOBr and sodium hydroxide. You should find what will be the final product. Here HOBr is there. HOBr separate it like Br minus and OH minus. Br plus will attack because starting metal is alkene. Brominium ion will form. Then brominium ion will break. You have two possibilities, primary and tertiary cation. Tertiary cation is more stable. OH attacks. You have OH and Br in the nearby carbon. Next step, you are using sodium hydroxide. It abstracts the proton, form oxygen anion. It can act as a nucleophile. Bromine also a good leaving group. It attacks. You have epoxide formation. The continuous possibility, continuous optimization to the product. The concept you outlined here is, if there is many functional group, consider intramolecular reactions. Then the next example, you have benzene attached with heterocyclic compound with 2 nitrogen and 1 SO2. You are heating it up very high temperature, and sodamide and ammonia you are using. You should find what will be the final product. Here the starting metal is interesting because it has two leaving groups, N2 and SO2. You are heating it up. It is a trigger for the reaction. So N2 and SO2 leaves, you have benzene. Why benzene means? Two leaving group in the 1,2 carbon leads to the benzene. Benzene is the benzene with one triple bond. Next step, sodamide and ammonia you are using. Immediately form amine there. The concept you outlined here is, whenever you have two adjacent leaving group in benzene, you will end up with benzene mechanism. Then the next example, you have benzene with three different functional groups, fluorine, bromine and nitro group, reacting with sodium salt of thiol. You should find what will be the final product. Here starting metal is thiol. It can attack bromine or fluorine. It is labeled as A and B. A attack leads to the anion away from the electron withdrawing group. B attack leads to the anion near NO2. NO2 is the electron withdrawing group. It can effectively stabilize the anion. Fluorine eliminates. You end up with the final product. This reaction is interesting because fluorine is the leaving group here. Why it is possible? Because priority is anion stability, not leaving group ability. The concept you outlined here is, even fluorine can act as a leaving group if the system is unstable. Then the next example, you have cycloheptane with alcohol and amine. You are reacting with nitrous acid. You should find what will be the final product. Here you are having amine, you are using the nitrous acid mean Temjanov reaction. Basically you are converting amine to N2+. It's a good leaving group because of nitrogen triple bond, but it need assistance. So ring open, you have N2 elimination with cation. Alcohol near cation mean you end up with carbonyl. The concept you outlined here is, Temjanov reaction is like Wagner-Mervin rearrangement. Cation forms and reduce the ring strain. Then the next example, you have benzene with fused with dicarbonate, which is also a peroxide attachment. You are reacting with light, sodamide and ammonia. You should find what will be the final product. Here you have peroxide. Peroxide can generate the radical with light because peroxide has lone pair ripples. It can easily break the bond, form radical. Two radical nearby, obviously ripples and high CO2 elimination is possible. It has two CO2 elimination in 1,2 position, leads to the benzene. Benzene is benzene with triple bond. You are reacting with sodamide and ammonia, form the amine there. The concept you outlined here is, peroxide can generate the radical with light. Then the next example, you have cyclohexanone. In third position, side chain you have acid. The reagent is phosphoric acid and base. You should find what will be the final product. Here you have acid. If you use very strong acid, it becomes acyl cation. It's a very important reagent. Converting acid into carbonyl cation is important. Next step is interesting. The cation can attack the enolate in presence of base. A enolate, B enolate is possible, but B enolate leads to the highly strainful ring system. According to Bayes' theory, 4-member itself very strainful, but additionally, you have one carbonyl which also need 120 degree, highly unstable. So, A removal is major. You end up with bicyclo compound, less strainful when compared to B hydrogen removal product. So, final product is diketone bicyclic product. Then the next example. Here you have amino acid which contain hydrogen and ethyl. You are reacting with sodium nitrate and HBr. You should find what will be the final product. Here amine group is there. You are using sodium nitrate. So diacetization kind of reaction is possible. N2 plus forms. N2 plus is a good leaving group because of nitrogen triple bond. So it can assist the leaving group. Bromine attacks. You have the final product. Why this reaction is important? It may look simple. Here, internal SNI mechanism because assistance come from internal group. N2 leaves, same side bromine comes. Instead of inversion in configuration, here retention in configuration happen. The concept you outline here is SNI mechanism, retention of configuration happen. Then the next example, you have amide, both sides attached with phenyl. You are reacting with nitric acid and sulfuric acid. You should find what will be the final product. Here aromatic electrophilic substitution. So electron density matter. A ring is electron rich because of amine, which is mesomeric in nature. B ring is electron deficient because of carbonyl group. It is sp2 carbon meta-director. You are using nitric acid and sulfuric acid. Where the attack will happen? Only A attack is major because of high electron density. So the P product is major. Q and R are minor because of electron density. Here Q you may consider it, but it has steric effect. Only P is the major product. The concept you outline here is aromatic electrophilic substitution controlled by electron density in the benzene ring. Then the next example, you have succinic acid. You are converting into ester and acid chloride. You should find the reagents and number of steps involved in the conversion. Here if you redraw with carbonyl, it will be easy. First step will be heating it up. Heating leads to the water removal, hence anhydride formation. Then methanol attacks the electrophilic carbon. You have ring opening. Ring open with ester and acid. Acid can be converted into acid chloride by SOCl2. You end up with desired product. The concept you outlined here is you should master the reagents and design the product with less number of steps. Then the next example, you have benzene, 2 aldehyde group in 1,2 position. You are reacting with sodium hydroxide. You should find what will be the final product. Here Cannizzaro reaction is possible since there is no alpha hydrogen. So sodium hydroxide attacks. Instead of intramolecular Cannizzaro reaction, intermolecular is possible because no collision is required. So hydride transfer occurs. You have O-, then O- quenched with alcohol. Further, the condition leads to the water elimination. Produce anhydride. So you start from dialdehyde, end up with lactone there. The concept you outline here is Whenever you have two aldehyde group in benzene, chances of intramolecular Cannizzaro reaction. Then the next example, you have dimethyl reacting with nitric acid and sulfuric acid. You should find what will be the final product. The reaction is interesting because it's a simple aromatic electrophilic substitution reaction. I mean, you may think it like electron donating group because of mesomeric nitrogen. Here it is not at all possible. Why? Because protonation leads amine into the quaternary ammonium salt. It is nitrogen with positive charge. It's a cation, electron withdrawing in nature. Direct the incoming group to meta position. So ortho and para will be minor. You may also consider dinitro substitution. Here dinitro substitution also not possible. Why? Because mononitration makes the ring electron deficient. So dinitration is not possible. The concept you outline here is nitration in the amine always happen in the meta position. Then the next example, you have linear chain compound with alkene, alcohol, 2-methyl group. You are reacting with iodine, sodium bicarbonate. You should find what will be the final product. Here alkene is there. You are using the iodine. It forms iodinium ion. You have internal nucleophile which is OH. To conceive the reaction, you have to redraw the molecule. If you redraw it, oxygen and 3-member ring is nearby. Oxygen can attack less hindered or more hindered position. It attack less hindered position. You have cation formation. Cation stability also dictate the reaction. Secondary cation is more stable. It formed, and you have nucleophile and cation nearby mean new CO bond. You started with linear compound, end up with cyclic compound. The concept you outlined here is the intermediate stability always decides the final product. Then the next example, you have benzoic acid. Ortho position you have side chain attached with phenyl group. You are using acidic condition. You should find what will be the final product. The reaction is Friedel-Crafts acylation reaction because you have acid and you are using acid also a catalyst. So water removal, acyl cation is possible. Acyl cation is possible. It can attack the nearby benzene ring. The acyl cation can attack anywhere in the benzene ring, but only ortho attack is favorable because of bond angle. So 7-member product is the major one. It forms fused system. Here intramolecular reaction is the only possibility because intermolecular reaction require collision there. The concept you outlined here is intramolecular Friedel-Crafts acylation is possible whenever you have two phenyl system and one acidic group. Then the next example, you have cyclohexene, it connected with amine, which is a reduced pyrrole. Basically it's a enamine. You are reacting with alpha, beta and saturated ketone, then acidic hydrolysis. You should find what will be the final product. Here enamine is there. Enamine can be a good nucleophile. It generates the anion. It can attack the alpha, beta and saturated ketone. Since the carbon ions are soft nucleophile, it will undergo 1,4 addition or Michael addition. So new CC bond forms. Finally you end up with alpha conjugation there. Hydrolysis remove the amine. That's why you got ketone. You end up with diketone. The concept you outlined here is carbon nucleophiles are soft. It will undergo 1,4 addition. Then the next example, you have benzene attached with nitro group and chlorine. You are reacting with potassium cyanide and ethyl alcohol. You should find what will be the final product. Here cyanide is the nucleophile. It can attack the benzene ring. Why? Because nitro group is electron withdrawing group, make the ring electron deficient. So ring is the electrophile, cyanide is the nucleophile. Attack happen, you have anion near nitro group. Since cyanide can attack anywhere, it will selectively attack chlorine because it has leaving group, as well as anion stability is promoted by the nitro group. Since nitro group is electron withdrawing, it can stabilize the anion. Finally, aromatization by chlorine elimination, you end up with cyanide substitution. It is an aromatic nucleophilic substitution reaction. It's an addition elimination reaction. Then the next example, you have cyclopentanol, alpha position cyclobutane connected in spiro form. You are reacting with concentrated sulfuric acid and heating it up. You should find what will be the final product. Here alcohol is there, acid you are using. Acid makes alcohol as a good leaving group, form the cation. Here cyclobutyl group is near cation. It can relieve the ring strain by ring expansion. Moreover, during the expansion, secondary cation become tertiary cation. So, two stability promoted. One is ring strain reduction, another is more stable tertiary cation. Then cation has to be quenched. Cation quenched by H plus elimination. Finally, you end up with alkene. The concept you outline here is whenever there is an intermediate, ring strain relieve itself by contributing the mechanism. Then the next example, here you have latone, 4-member cyclic ester reacting with two different reagents. One is methyl magnesium bromide in acidic condition, another also with same condition, additionally copper chloride added. You should find what difference it can make. One is methyl magnesium bromide, another is with copper chloride. Here copper chloride makes the nucleophile soft. Methyl magnesium bromide, naturally it is a hard nucleophile. Hard nucleophile attacks the carbonate, ring open, because O minus acts as a leaving group. Then H plus attacks, you have alcohol, you end up with ketone. On the contrary, copper makes methyl group softer, so it attacks the carbon, you end up with acid there. Because ring open in the sideways, O minus forms, H plus attack, linear acid. Basically, it's a chemoselective reaction. Methyl magnesium attacks the carbonate, copper with methyl magnesium attacks the carbon. The concept you outline here is you can tune the nucleophilicity by the addition of copper in the Regnard reagent. Then the next example, you have cyclic compound with sulfur and oxygen. It's a 6-member ring. You are reacting with sodium hydroxide, bromine and chlorine in ethylene. You should find what will be the final product. Here two important things is there, regioselectivity and chemoselectivity. You are using the base abstract the proton, but there is a two possibility, A and B. A is the major here because sulfur is the big molecule, it stabilizes the anion by backbonding more than oxygen. So proton abstraction near the sulfur is major, near the oxygen is minor. Then anion attacks the halide. It can attack bromine carbon or chlorine carbon. Bromine is the good leaving group, so attack happen on the bromine carbon. It forms new CC bond. The reaction is the combination of regioselectivity and chemoselectivity. The concept you outline here is sulfur can stabilize the anion. Bromine is the good leaving group, then chlorine. Then the next example, you have halide, but it is a bridged system. It's a bicyclic compound. You are reacting with OH minus. You should find the reaction can undergo SN1 or SN2 mechanism. If you redraw nicely, you end up with bicyclic system. You can achieve it by writing with proper bond angle with one rigid carbon. Here SN1 mechanism you end up with carbocation. Here carbocation cannot form. According to Britt's rule, carbocation cannot form at the rigid carbon because of ring rigidity, and cation need the 120-degree angle. So SN1 possibility is not there. And SN2 mechanism is like stereospecific. It only attack the backside, but here backside is very crowded because of ring rigidity. Carbons are nearby and backside, so SN2 mechanism also not possible. So the concept you have to learn here is, in rigid carbon there is no SN1 and SN2 reaction. Then the next example, you have benzene, side chain you have alkyl and alkene. You are using acidic condition. You should find what will be the final product. Here starting metal is benzene, alkene and alkyl. H plus you are using. H plus can attack loosely bound alkene, not the benzene ring. But the attack has two possibilities, A and B. A leads to the major product because it can form stabilized cation. Then the cation attacks the ring. Why? Because it is like electrophilic aromatic substitution reaction. Cation is the electrophile. It can attack. So Fiedel-Crafts alkylation is possible. Acidic condition, cation, definitely ring substitution. The attack happen on ortho or para. Ortho is nearby. Bond angle and ring strain also allow it. So ortho attack is favorable. You end up with ortho substitution. If you read nicely, you end up with final 6-member benzene ring and 5-member pentane ring. The concept you have to learn here is, cation formation in the long chain benzene ring means there is a possibility of Fiedel-Crafts acylation. Then the next reaction, you have benzene with aldehyde and alcohol. We are reacting with sodium hydride and alkene, which is vinyl phosphine compound. You should find what will be the final product. Here you have alcohol and aldehyde. We are using the hydride. Hydride is the strong base. It abstracts the proton from oxygen. Oxygen anion can be a nucleophile. So it attacks the phenyl. It forms halide kind of compound. Phosphine can stabilize the negative charge. So it can act as the nucleophile. It attacks. Intramolecular Wittig reaction is possible. The attack leads to the ring closure, which forms stable 6-member one. Here intermolecular reaction also possible, but intra is the major product because there is no collision is required. Then phosphine and oxygen nearby. You have finally alkene formation. The concept you have to learn here is, halide also nucleophile. It can act intramolecular way and promote the Wittig reaction. Then the next example, you have dialder, which is 1-2 position. First position you have cyclopentane. Second position you have dimethyl group, and you are using acidic condition. You should find what will be the final product. Here diol is there. You are using the acidic condition. Basically phenol rearrangement. First step, acid attacks the alcohol. There is two possible water elimination. Acid attacks one alcohol or two alcohol. Two alcohol attacks leads to the stable cation, which is tertiary cation. Then the cation near the strainful 5-member ring. So ring tried to expand itself, ring expands. You have cation near the alcohol. If you read nicely, you could see 5-member ring becomes 6-member ring. Ring expansion happened. Then cation near the alcohol leads to the carbonyl. The concept you have to learn here is, here two types of stability is achieved. One is ring strain is released, another is stable cation is formed. Both factors guided the final product. Then the next example, you have benzene attached with alcohol. You are reacting with sodium hydroxide and methyl iodide. You should find what will be the final product. Here you have two acidic hydrogen. One is from acetylene, another is from alcohol. Both can form the nucleophile. One is O nucleophile, another is C nucleophile. O nucleophiles are weaker because it reduces the electron density due to the electron negativity. So carbon can be a better nucleophile than oxygen. So it attacks, you have new CC bond, methylation happen. So C alkylation is the major product here. The concept you outline here is electronegativity also can decide the nucleophilicity because it can reduce the electron density, reduce the nucleophilicity. Then the next example, you have linear chain compound with tertiary butyl group, methyl group and alcohol. You are using sulfuric acid. You should find what will be the final product. Here alcohol is there, acid you are using, hence chances of Wagner-Merwin rearrangement. First step will be attack of H plus to OH. It will make cation formation by water elimination. Then the cation is secondary cation. It can become tertiary by methyl migration. So methyl migrates, you have tertiary cation. Then tertiary cation has to be quenched. It can be quenched by nearby hydrogen or methyl hydrogen. Nearby hydrogen is effective because it forms more substituted alkene. It's a regioselective reaction. Basically, it's a say-up rule. More substituted alkene will form. The concept you outline here is during the cation quenching, always say-up rule dominates. Then the next example, you have tecline, it's a epoxide. In the connected carbon, you have trans-methyl groups. You are using sodium thiophenoxide. You should find what will be the final product. This reaction can be easily understood by drawing in the chair form. So draw the chair form, draw the trans-methylene group and epoxide. One methyl group is cis to epoxide, another is trans to epoxide. Here S minus attacks, which is nucleophile. It can attack both sides of epoxide, but it attacks the second carbon because it needs axial position. Since the mechanism is SN2 mechanism, it needs axial position. Epoxide also formed from the syn bond. One is axial, one is equatorial. So only on second position axial is free, attack happened. If you redraw nicely, you end up with final product, which is alcohol and thio group trans to each other. Two methyl groups are unaffected. The concept you outline here is in cyclic system, SN2 reaction require axial and steric free position. Then the next example, you have linear compound which is diketone. Terminal position you have alkene. You are reacting with base. You should find what will be the final product. Here you have many alpha hydrogen and base you are using. Chances of aldol condensation. Basically it's a proton abstraction in the first step. Only primary anion forms because primary anions are stable. Here stable anion form which form as the nucleophile. Here stable anion form between carbonyl and alkene because carbonyl can stabilize it by electron withdrawing. Alkyne can stabilize it by delocalization. So it is the nucleophile. Then nucleophile attacks the carbonyl. You have ring closure. If you redraw nicely, you have 5-member ring with hydrogen and oxygen nearby. If you eliminate it, you end up with conjugated alkene and conjugated ketone. So finally, driving force is conjugation. The concept you outline here is if there is many alpha hydrogen in aldol reaction, always look for the stable anion which will act as a nucleophile. Then the next reaction, starting metal is diketone. You are reacting with halide, which is dibromine. You are reacting with sodium ethoxide and ethanol. You should find what will be the final product. This reaction is interesting because of many possibilities. First step will be formation of anion, or you can say nucleophile. Nucleophile can attack the halide, you form new CC bond. Then again proton abstraction is possible. Again attack and halide leads to the fused system, which is 5-member system. So 5-member system with diketone. Again it has alpha hydrogen. It abstracts, it attacks. You have new fused 2 5-member system. Then hydrogen and alcohol is nearby. Water elimination is possible. Finally, you end up with conjugated ketone. Starting metal to product is completely unpredictable. All is driven by basics. The concept you have to learn here is aldol reaction continues until the presence of alpha hydrogen. Then the next example. Here you have dicarbonyl system. One is ketone, another is ester. You are reacting with sodium borohydride. You should find what will be the final product. Here sodium borohydride is the reducing agent. It provides H- which is nucleophile. Thing is that where it will attack ester carbonyl or ketone carbonyl, or both can be attacked. The fact here is reactivity difference. Carbonyl is more reactive because ester has lone pair oxygen nearby. It reduce the positive charge on the carbonyl. So positive charge reduce, it will be weaker. So the three possibilities I given PQ R is the major product, only ketone is reduced. P is minor because low reactive ester is reduced. Q is also minor because both is reduced. R is the major product. Here you should know that BH bond is stronger, so it cannot donate H plus easily. So borohydride is the weak reducing agent, only reduce the reactive carbonyl, not the ester. The concept you have to learn here is ketones are more reactive than ester. Then the next example, you have cyclohexane. Alcohol and methyl group is there. Second position you have cyclopropane. It's a spiro compound. You are reacting with HCl. You should find what will be the final compound. Here you have alcohol. You are using the acid. Acid makes alcohol as the good leaving group. So it forms cation. So cyclopropyl group is nearby. It is very strainful system. Cation is also nearby. So ring try to reduce its strain, expand itself. So 3-member ring become 4-member. During the transition, secondary cation become tertiary cation. If you read down nicely, you have fused system. Then chlorine attacks, cation quenches. The concept you have to learn here is whenever there is a strain in the system, if intermediates form, the strain will relieve itself. Then the next example, you have cyclopentanone. Second position you have 2 methyl groups, ammonium hydroxide and sulfuric acid you are using. You should find what will be the final product. Here you have chances of Beckmann rearrangement because hydroxylamine form oxime with ketone, so it form oxime. Oxime form trans to methyl group to avoid the steric effect. In Beckmann rearrangement, always trans group migrates. So first step will be OH removal. OH will remove as the water H2O. Then migrating group assists the leaving of H2O. You have cation in the alkene there. Then if you read down nicely, you end up with 6-member ring with cation. Then OH attacks, you have enol. Then there is a tautomerism kind of thing. Then tautomerism happened, you end up with amide. Starting with ketone, 5-member, end up with 6-member amide. The concept you have to learn here is in Beckmann rearrangement, always trans group migrates. Then the next example, you have cyclohexane and cyclopentane, both connected through double bond. You are using hydrogen peroxide and sulfuric acid. You should find what will be the final product. Here chances of phenol-phenolone rearrangement because alkene is there. you are reacting with hydrogen peroxide. It forms diol. So alcohol in acidic condition, chances of cation formation. Both alcohol can be removed, but alcohol near cyclohexane will be removed. Why? Because it will remove the strain in the system. So H2O eliminates, you have cation. So H2O forms and ring open assist the H2O elimination. Cation formed near the alcohol. It becomes the spiro compound with two 6-member ring. You can see it very clearly if you redraw the ring. So you have cation near the alcohol, end up with ketone. The concept you outline here is in phenol-phenolone rearrangement, two cyclic products end up with spiro compound. Then the next example, you have benzoic acid, you are using SOCl2, sodium acid, heating it up, then methylamine. You should find what will be the final product. Here you are having benzoic acid, you are reacting with SOCl2, it's a chlorine donor, it converts acid into acid chloride. Next step you are using sodium acid, it converts chlorine into acid, again a functional group conversion. Then you are heating it up, acid in heating condition, Curtius rearrangement, because N2 is the good leaving group, so phenyl group migrates, N2 eliminate. You have isocyanate, then amine attacks, you have new CN bond. It's a kind of enol. If you redraw nicely, you end up with amide there. The concept you outline here is whenever you have acyl acid in acidic condition, you end up with Curtius rearrangement. Then the next example, you have cyclohexenone. Third position, you have methyl group. You are reacting with dimethyl copper and methyl magnesium chloride and allyl chloride. You should find what will be the final product. Here copper you are using, methyl magnesium chloride you are having. So soft nucleophile formation. Copper based nucleophiles are soft. It form 1,4 addition or you can say Michael addition. Hence attack leads to the anion formation at the second position. Minor will be 1,2 addition which is attack on methyl group on carbonate. So major will be 1,4 addition. So anion form. Since there is no quenching pathway, anion can act as a nucleophile. It can attack chlorine. You have new CC bond. The mechanism can be SN2 prime also. For simplicity, I given straightforward reaction. The concept you outline here is copper based carbon nucleophiles are soft. It will undergo 1,4 Michael addition. Then the next example, here you have ether, one side phenyl, another side alcohol, and you have epoxide below the plane. You are reacting with sodium hydroxide and tertiary butyl thiol. You should find what will be the final product. Here you are having alcohol, base you are using, it abstracts the proton, it can act as a nucleophile. In the system, epoxide is there. Internal nucleophilic attack is possible, ring open. The interesting fact here is the mechanism is SN2, so the attack is from backside. Since epoxide is below the plane, attack happen on above. You form epoxide above the plane. Then thiol attack. Again it is a SN2 mechanism. It can only attack from the less hindered side. So less hindered side attack happen. You have new CC bond. End up with final product. The concept you outline here is SN2 reaction required backside attack as well as less steric attack. Then the next example, you have benzene and propyl chloride, aluminum chloride you are using. You should find what will be the final product. Here aluminum chloride you are using. Aluminum chloride can abstract the proton, form cation. Once the cation is formed, it tries to stabilize itself. It is called Wagner-Merwin rearrangement. So primary cation is there. It will convert into secondary cation by hydride transfer. You end up with electrophile which can attack the benzene ring. So you have rearranged attack on the benzene ring. It form isopropyl benzene. The concept you have to learn here is whenever there is an intermediate cation, you should always think of its stability and expect Wagner-Merwin rearrangement. Then the next example, you have cyclohexane and you have hydrazine which is fused with carbonate reacting with methyl lithium and ether. You should find what will be the final product. Here it is a sapphire elimination. It's an interesting naming reaction. Basically, we are generating the nucleophile from the side chain. First step will be abstraction of proton. There are many proton is there, but acidic protons reacts quickly. So proton and nitrogen, proton and alpha position get removed. Then charge travels. You have tosylate elimination. Here N2 is there. N2 also a good leaving group. So charge travels. Again you end up with enanion. Enanion can be quenched with H+. You end up with alkene. You're starting from cyclohexane. You end up with cyclohexene. The concept you have to learn here is sapphire elimination is a functional group conversion reaction. Alkene formed from the loss of hydrazine. Then the next example, you have toluene. First step you are using chlorine and light. Second step you are using HCN and ethyl alcohol. Third step H plus and H2O. You should find what will be the final product. Here toluene is there. It has sp2 and sp3 carbon. Light and chlorine you are using. It can generate the radical. Here radical at methyl is stable because electronegativity of sp3 carbon is less. So attack happen on side chain, not on the ring. So side chain substitution is major. Chlorine attacks. You have benzyl chloride. Then cyanide attack. It's a functional group transformation. Chlorine becomes cyanide. Then acid hydrolysis you are using. It converts cyanide into acid. The concept you have to learn here is without proper Lewis catalyst, activation of benzene is not possible. So side chain reactions happen. Then the next example, you are reacting with cyclopentene. Reagents are bromoform and NaOH, aqueous silver nitrate. You should find what will be the final product. Here bromoform and NaOH is the important reagent because bromoform form carbene. Carbene can be captured by alkene by the insertion reaction. Since 2 bromine is there, cyclopropyl bromine forms. Next step you are using silver nitrate. Silver nitrate can abstract the bromine. It forms cation. Then ring try to open itself to reduce the strain. Ring opens, 5-member ring becomes 6-member ring. If you redraw nicely, you end up with cation near the bromide. Then water attacks, you have alcohol there. The concept you have to learn here is bromoform in the basic condition form the carbene. Then the next example, here you have ketone. Both sides you have cyclohexane. NaOH and Br2 you are using. You should find what will be the final product. Here base you are using, ketone is there. So possibility of nucleophile. It can attack the next reagent which is bromine. It form new CPR bond. Then same basic condition can promote the Favosky rearrangement. Anion which is nucleophile form which attacks the benzene. You have cyclopropanone. Then base you are using, base attacks, ring open, you have the acid there. Here starting material and product is rearranged. One carbon go out of the system. The concept you have to learn here is alpha haloketone undergo Favosky rearrangement. Then the next example, you have linear chain compound contain thiol, alcohol, bromine. You are reacting with base OH minus. You should find what will be the final product. Here base you are using. Base can abstract the proton. It can abstract from oxygen as well as sulfur. But which will be the dominant one? Here basically we are generating the nucleophile. Which nucleophile can donate the electron? Because nucleophilicity is decided by electron density. Oxygen is electronegative, cannot donate the electron willingly. So obvious choice will be sulfur. So sulfur attacks, bromine eliminates. Intramolecular nucleophilic attack will be there. So you have cyclic compound. If you redraw nicely, 5-member sulfur ring with side chain alcohol. The concept you got learned here is sulfur is better nucleophile than oxygen because of oxygen high electronegativity. Then the next example, you have chiral compound with hydrogen, acid chloride, ethyl and methyl group. You are reacting with sodium azide and NaOH and heating it up. You should find what will be the final product. The answer in the Cartier's rearrangement. First step will be conversion of acid chloride into azide. Chlorine replaced with N3. Then you are heating it up. Azide with heating promote the Cartier's rearrangement because N2 is the good leaving group. The group on carbon migrates. Here you have new NC bond and an isocyanate. Here the important thing is chiral carbon migrates. There is no change in the configuration. Retention of configuration happen. It also gives the possibility of concerted reaction. It migrates. Then you have carbonate. Water attacks. You have COOH. Then heating leads to the CO2 elimination. Finally end up with amine. Two important things happen here. One is conversion of acid chloride group into amine. Second is chiral carbon did not change its configuration during the reaction. Then the next example, you have para-aminophenol reacting with acidic anhydride, 1 equivalent. You should find what will be the final product. Here you have two nucleophiles, oxygen and nitrogen, which will attack the carbonyl is the real question. Or you can say question is about nucleophilicity, nitrogen or oxygen. When compare the electronegativity, oxygen has higher one, nitrogen is lower one. So oxygen cannot donate the electron willingly. The definition of nucleophile is high electron density donor. So oxygen cannot be a better nucleophile than amine. So amine attacks, you have the final new NC product. It is also a part of chemoselectivity because you are choosing amine over alcohol. That's why it's called chemoselectivity. The concept you outlined here is amine is the better nucleophile than alcohol. Then the next example, you have quinone with alpha position 2 methyl groups. You are reacting with conjugated diene and amine. Further hydrolysis at temperature. You should find what will be the final product. Here the problem in the blind side. Why? Because it's a Diels-Alder reaction. Diene and dienophile situation. Diene, if you read it nicely, you are having cis diene with amine group. Amine group is quaternary ammonium salt. It's electron withdrawing. And you have dienophile, which is with 2 electron withdrawing group, carbonyl. So it should be a dienophile. So dienophile situation leads to the 4+2 cycloaddition. Here important thing you should note here is addition is syn addition. Hence methyl and hydrogens are syn to each other, or you can say cis to each other. Then hydrolysis leads to the amine oxygen condensation, leads to the imine there. The concept you outlined here is you always imagine the reaction. Here Diels-Alder reaction is hidden with structural arrangements. Then the next example, you have linear compound with alkene and acid. You are using iodine and water, sodium bicarbonate. You should find what will be the final compound. Here you have alkene and acid. If you read that nicely, there is a possibility of cyclization because you are using the base. Base abstract the proton, create the nucleophile, and next step you are using iodine. Iodine promote the iodination reaction, so it forms strainful 3-member ring. Already you have oxygen nucleophile in the system. It attacks, ring open, you have new cyclic product with side chain iodine. The probability of intramolecular reaction is higher when compared to intermolecular because there is no collision required and the atoms are readily available. Final product is intramolecular product. The concept you outlined here is you should master the fundamentals to master the organic conversion. Then the next reaction. Here you have decline, carbonyl and methyl group in the system. You are using hydroxylamine and sulfuric acid. You should find what will be the final product. Here you have ketone. You are using the hydroxylamine. It will form oxime. Here oxime form trans to the methyl group because of steric effect. Then the acidic condition promote the Beckmann rearrangement. In Beckmann rearrangement, trans group migrates. Here if you look at it, trans group is the ring carbon. So it migrates. You have ring opening. 6-member ring becomes 7-member ring with cation. Then cation quenched with alcohol. Then hetoenol tautomerism occur. You have finally amide there. Start with ketone, end up with amide. Start from 6-member, end up with 7-member. Finally, you have rearranged product. The concept you outlined here is in Beckmann rearrangement, always trans group migrates. Then the next example, you have benzene, side chain you have methyl and ketone. You are reacting with peracid. You should find what will be the final product. By looking at the peracid, you might realize it's a Bayer-Villiger oxidation rearrangement reaction. First step will be attack on nucleophile. Nucleophilic addition to the carbonyl happened. You have new CO bond. The OO bond is weaker, good leaving group. So the migrating group moves. You have new CO bond. It leads to the cation near the alcohol. You end up with ketone there because cation near the alcohol convert into ketone by losing hydrogen. Finally, you end up with ester. You are starting from ketone, end up with ester with complete rearrangement. Here one thing you might have noticed is no change in the chiral carbon because retention of configuration happened. Here migrating group can be methyl or the ring. Ring is migrates because intermediate is electron deficient, hence electron rich group migrates. The concept you outlined here is in Bayer-Villiger oxidation reaction, always electron rich group migrates. Then the next example, you have benzene, vinyl chloride you are using, aluminum chloride as a catalyst. You should find what will be the final product. Here you might have predicted as Friedel-Crafts alkylation, but here it is not at all possible. Why? Because chlorine attached with the sp2 carbon, leaving up chlorine is not easy. Why? Because bond length is smaller, chlorine removal is not that easy. So electrophile is not formed, no reaction. It is not feasible. Another similar factor is cation on the sp2 carbon also highly unstable, so it won't form. So two factors don't allow the chlorine elimination, so no reaction. So this organic conversion is about possibility of the reaction. In vinyl chloride, there is no Friedel-Crafts alkylation reaction. Then the next example, you have benzene and you have continuous nitrogen in the ring with amine. You are using nitrous acid, sodamide and ammonia. You should find what will be the final product. Here amine is there, nitrous acid you are using, it formed diazonium salt. Here consecutive nitrogens are there, both will be the good leaving group. So 2N2 elimination. Since nitrogen-nitrogen triple bond is stronger, it promotes the N2 elimination. Make the N2 as a good leaving group. It leaves, it form benzene. Benzene is the benzene with one triple bond. Then sodamide and liquid ammonia you are using. End up with aniline. The concept you outlined here is whenever you have 1,2-di leaving group in the benzene, it will be a benzene source. Then the next example, you have 1,3-diketone which is in the cyclohexane. You are reacting with sodium hydroxide and iodine. You should find what will be the final product. Everybody knows methylene between diketone is the active methylene group. Sodium hydroxide you are using mean it will form nucleophile. Then nucleophile attacks the iodine. You have new C iodine bond. Then base you are using. Again base abstract the proton. You have again iodine attachment. Then 2 iodine in the system is unstable. Then you have sodium hydroxide attack in the system. The attack leads to the ring opening. Again it forms nucleophile. It attacks again iodine. You have triiodide. Then it is like iodoform reaction. Without COCH3, it converts into acid there. So CHI3 is the leaving group, which is iodoform. You end up with diacid. The concept you have to learn here is always master the fundamental reactions. Then the next example, starting metal is dialkyne. You are reacting with butyl lithium epoxide in acidic condition. You should find what will be the final product. Here butyl lithium you are using, it's a strong base, it abstracts the proton. So 3 proton abstraction is possible, but only one can act as a nucleophile because of hybridization. Electronegativity, if you look at it, sp carbon is more electronegative, sp3 carbon is less electronegative because of S character. So sp carbon, which is alkyne carbon, cannot act as a nucleophile. On the contrary, alpha carbon, which can become a nucleophile, which attacks ring open. So the major product will be sp3 carbon generated nucleophile, attack the epoxide, form linear alcohol. The concept you have to learn here is nucleophilicity is controlled by hybridization, that is really by electronegativity. Then the next example, you have benzene, it attached with lactone. You have 2 different ring opening. One is just a ester opening to acid, another is ester to alcohol and acid. Basically similar reaction, different ring opening. You should find reagents and number of steps involved in the conversion reaction. Here you have 2 types of ring opening, A break and B break. A break leads to the desired product, B break leads to the acid and alcohol. The reagent is acid hydrolysis. Simple reagent everybody known as acid hydrolysis, which open the ring, you have acid and alcohol. On the contrary, if you want to break carbonyl carbon, you should use palladium carbon and hydrogen, which breaks CO bond, which in turn form a acid and alkane. So finally end up with desired product. The concept you have to learn here is the control and understanding of reagents are important. Here 2 different product is achieved from the same reactant by the 2 different reagents. Then the next example, you have decline, amine and alcohol is there. Methyl and hydrogen trans to each other. NaNO2 HCl you are using. You should find what will be the final product. The problem can be easily understandable by drawing in the chair form. So we draw the decline chair form. Here NH2 is the functional group. You are using NaNO2 HCl. It's a diacidization reaction. Basically N2 plus formation. Then N2 is the good leaving group. So assistance of N2 leaving is required. So hydrogen acids, you have alkene with N2 elimination. So alkene formation is really a enol. If you do tautomerism, you end up with ketone. So if you redraw nicely to the planar form, you end up with ketone there. So you start with amine and alcohol, end up with ketone. The concept you have to learn here is NH2 become a leaving group if you use NaNO2 HCl. Then the next example, you have bromofluorobenzene reacting with magnesium ether and anthracene. You should find what will be the final product. Here you are using magnesium, halides are there. So chances of Grignard reagent formation, which will form bromine or fluorine. Bromine form, that is the basic reactivity of halide. So methyl magnesium bromide forms. Then it has to be quenched. Fluorine acts as a leaving group. Yes, you had it correct. Fluorine as a leaving group. You end up with benzene. So starting metal is sources of benzene. Then benzene can act as a electrophile. So anthracene considered as diene. Benzene is dienophile. So 4 plus 2 cycloaddition till Alder reaction happen. Here middle benzene ring is weakly reactive because of annihilation effect. Annihilation means individual ring aromaticity. Only middle ring is weaker in terms of aromaticity. The concept you have to learn here is even fluorine can act as a leaving group if the charge quenching is required. Then the next example, you have benzoic acid. Second position, you have alkyne in the side chain. You are using sodium and ammonia. You should find what will be the final product. Here benzene is there, alkyne is there. Chances of pitch reduction as well as alkyne reduction. The reaction shown as two steps. First step will be pitch reduction. Pitch reduction always reduction happen near the electron withdrawing group because intermediate is the anion. So 1,4 reduction happen near to the acid group as it is electron withdrawing. You have 1,4 reduction. Then if you look at the side chain, it is the alkyne. Sodium and ammonia you are using in which leads to the radical anion formation, stereoselective in nature because it forms only transalkene. The concepts like stereoselectivity and regioselectivities are important while doing organic conversion reaction. Then the next example, here you have fused system, alkene in the connected carbon, you have heterocyclic nitrogen and 3 methyl group. You are reacting with bromine and KOH. You should find what will be the final product. Here you have imine. Imine can generate the nucleophile which in turn attacks the bromine. So you have new CBr bond. Then cation is there. Cation can be unconnected carbon. Alcohol attacks. You have alcohol. Here bromine is there. Alcohol is there. Both are nucleophile. But nitrogen is the better nucleophile because nitrogen can donate the electron easily and oxygen cannot donate the electron easily due to high electronegativity. So nitrogen attacks. You have new ring formation but the ring is weaker because of smaller size. The ring opened by the ketone formation. So you finally end up with unusual unexpected product which is pyro compound. You are starting from fused compound, end up with pyro compound. The concept you have to learn here is nucleophilicity and electrophilicity are inevitable if you want to do organic conversion reaction. Then the next example, you have conjugated ketone which is alpha, beta unsaturated ketone. You are reacting with two different reagents, alkyl lithium and thiol. You should find what will be the final product. Here alkyl lithium and thiol you are using. Thiol will be the soft nucleophile because sulfur is big, polarizable, often considered as soft, so it will undergo 1,4 Michael addition. On the contrary, lithium is hard, which generate the hard nucleophile. So alkyl generated from lithium is hard. It attacks the 2 position. So 1,2 attack happen in terms of alkyl lithium. It forms alcohol. On the contrary, thiol attacks the 4th position. You have anion at O minus. Then it quenched with H plus. End up with enol. Then enol converted into ketone there. So one is 1,2 addition. Another is 1,4 addition. The concept you have to learn here is sulfur nucleophiles are soft. It will undergo 1,4 Michael addition. Then the next example, here you have cyclohexene, acid and methyl group is there, acid is above the plane, methyl is below the plane, you are using iodine and NaOH, you should find what will be the final product. Here the problem can be easily understandable if you redraw to the chair form. If you redraw it, you have acid which is near to the alkene which creates the steric effect. Next step, iodine attacks the alkene. It forms iodinium ion. Iodinium ion form below the plane because to avoid the steric effect. So you have acid which can be a nucleophile. Even though it's a weak nucleophile, it can act as a nucleophile. It can attack 2 positions, 6 and 7, but it attacks 7 position because of ring rigidity. Ring rigidness don't allow the 7th position attack because oxygen has to stretch more. If you redraw nicely, you end up with bicyclic compound. The concepts like steric effect, ring rigidity, and regioselectivity are important while you do organic conversions. Then the next example, you have 8-member cyclic compound which contain 3 functional groups: ketone, ether, alkene, reacting with HCl. You should find what will be the final product. Here alkene is there, acid you are using. Acid can attack 1 and 2 position, but attack on the 1 position is favorable because of the ring size. 2 position leads to the ring size, which is 4-member ring, highly strainful. So only one attack is possible. Basically oxygen is assisting the reaction. So it attacks, then chlorine comes. Chlorine can open the ring. It end up with completely unexpected product. Ring is contracted from 8-member ring to the 5-member unusual ring. This reaction is all about basics. It involves cation stability, neighboring group participation, and nucleophilicity. Then the next example, you have cyclohexanone, side chain you have bromide, you are using the phosphine and sulfur oxide with the salt of sodium. You should find what will be the final product. Here you have halogen which is bromide, you are using the phosphine which leads to the substitution reaction which is phosphine reaction. Phosphine form as a cation, so it is a electron withdrawing group. The hydrogen becomes acidic, it is abstracted by CH-. You end up with nucleophilic carbon. Since you have internal electrophile, nucleophile attacks, you have ring formation. If you redraw nicely, you have new 5-member reaction. So phosphine and oxygen in the same system, definitely intravitic reaction. So phosphorus oxygen forms, you have alkene there. The concept you outline here is whenever you look sulfur and sulfoxyhalide, you might realize there is a chances of Wittig olefination reaction. Then the next example, here you have benzene. In 1,4 position you have alcohol and COOCH3. You are converting into cyclohexanone, 4th position CH2OH. You have to find this organic conversion, reagents involved in it, and number of steps involved in it. There are many possible reaction pathway. Here I given meaningful one. First step will be nickel hydrogen reduction on benzene ring because that is the final product without aromaticity. So you have alcohol and ester. Then if you are using PCC, alcohol will become ketone. Here ketone and esters are same reactivity. Here ketone and ester. Ketone is very reactive, so we have to protect it. So diol you are using, ketone is protected. So only reaction happen with ester is possible. If you reduce it, you end up with alcohol. Then if you deproduct it, you have desired product. The concept you outline here, you should master the reagent and master the production and deproduction to master the organic conversion reaction. Then the next reaction, you have bicyclic compound with chlorine. You are using tin tetrachloride. You should find what will be the final product. Here you have chlorine, tin tetrachloride. It will act like a Lewis catalyst, abstract the chlorine. So you have cation formation. Whenever there is a cation formation, chances of Wagner-Mervin rearrangement, non-classical carbocation is possible. Since the carbon is bridged carbon, non-classical carbocation is possible. You end up with cation near the 6th carbon. Then if you redraw nicely, you have completely rearranged product with cation position. Then chlorine attacks. Chlorine can attack endo or exo. Exo is major. It has less steric effect. The concept you have to learn here is in bicyclic system, cation always move towards non-classical carbocation. Then the next example, you have acetaldehyde and vinyl cyanide. Phosphine you are using. You should find what will be the final product. Here phosphine you are using. Phosphine can generate the nucleophile through Bayes-Hillman reaction. It's an unusual nucleophile generation because carbon near electron withdrawing group make it as an active carbon. It can generate the nucleophile. So nucleophile can attack carbonyl. You have new CC bond. Then you have phosphine in the system which can be removed by hydrogen removal. Further phosphine elimination. So if you look at clearly, you have connected acetaldehyde and vinyl cyanide through single carbon by nucleophile generation. It is a very unusual reaction because alkene and aldehyde form new CC bond. The concept you have to learn here is Bayes-Hillman reaction form unusual nucleophile which will promote alkene and aldehyde bond formation. Then the next example, you have epoxide, 2 phenyl in the same carbon. You are using the acidic condition. You should find what will be the final product. Here epoxide is there. You are using the acidic condition. So O attack the hydrogen, form the alcohol with cation. The ring has to open. Regioselective ring opening. Cation form near the phenyl group because phenyl can stabilize it by resonance. So cation form, but there is no quenching pathway. So hydrogen migrates. Cation form near the alcohol. Then alcohol quenched as the ketone. You end up with unexpected product. The concept you have to learn here is in epoxide ring opening, regioselectivity decided by cation stability. Then the next example, the starting metal is in question. You are converting into bicyclic product which is O-benzyl group and lactone and alkene. You are using MCBPA, metachlorobenzoic acid. You should find the reactant here. The reaction is basically finding the reactant. So we will go from reverse. You have ester there. You can generate it from ketone which is Baeyer-Villiger oxidation. It is perfect for bicyclic compound. So if you start from the ketone, acetate attacks, you have nucleophilic addition to the carbonyl. Then electron rich group migrates. So ring carbon migrates. You have ring expansion with cation. That cation form near the alcohol. If you redraw nicely, you end up with lactone there. Alcohol become carbonyl. It is cyclic ester. So lactone. So you find the starting material by the simple Baeyer-Villiger oxidation reaction. It's a rearrangement reaction. Ketone to ester conversion. The concept you have to learn here is in Baeyer-Villiger rearrangement, electron-rich group migrates to quench the cation. Then the next reaction, you have chlorobenzene with methyl group. Side chain you have secondary amine. You are using phenyl lithium. You should find what will be the final product. Here you are using the phenyl lithium. Phenyl lithium is the strong base. It abstracts the proton which will form anion. It will be quenched by Br elimination. Basically it's a benzene with one triple bond. It is a elimination addition reaction. Since you have internal nucleophile, it attacks, you have new NC bond. The attack happen on the two sides of the benzene. One is 6-member ring formation, another is 7-member ring formation. But 6-member ring is stable, so attack happen on the first carbon. Attack leads to the fused system. Basically, the regioselectivity happen. You are choosing one carbon over another. The concept you have to learn here is intramolecular addition elimination reaction is possible. Then the next reaction, Here the compound is given with Fischer projection. Phenyl groups trans to each other. You have benzyl and acid at terminal. You are reacting with HF. You should find what will be the final product. Here you have acid, phenyl, many functional group, but the problem in the blind side. Basically, it's a Fiddle-Crafts kind of reaction. Since you are using the strong base, acid can generate as the acyl cation, which in turn attacks the benzene ring, which is on the Fischer projection. If you redraw, you know the possibility of aromatic electrophilic substitution reaction. So it attacks, you end up with final product. Here attack can happen on ortho and para, but ortho leads to the stable 6-member ring. Phenyl maintain its position as a trans position. Both phenyls are trans to each other. The concept you outline here is even acid become acyl cation if you use the strong acid like HF. Then the next reaction, here you have ketone, one side naphthalene, another side you have triphenyl carbon. You are reacting with acid. You should find what will be the final product. The reaction is all about stability. First step will be attack of acid on carbonyl, which leads to the cation on the carbon. The cation can be better stabilized by phenyl group. So phenyl myriads create the superior cation because the cation stabilized by delocalization in phenyl group. Extra stability by 2 phenyl group achieved. Then it can act as a electrophile. It attacks the benzene ring. You have new fusion. Here attack only on alpha position is possible because ring rigidity and bond don't allow the higher ring size here. So it is a regioselectivity along with the rearrangement reaction. Then the next reaction. Here you have cyclohexanol. Second position you have methyl. Fifth position you have isopropene. You are reacting with HBr and NeOH. You should find what will be the final product. Here acid you are using. Acid can attack the alkene. It forms cation. There is a two possibility, hence regioselectivity. Primary and tertiary cation can form, but tertiary is more stable. It forms as a major. Then hydrogen eliminates. You have the alkene there. Again, two hydrogen elimination is possible, but most substituted alkene is stable. It forms. You have alkene there. Then base you are using. Base can mobilize the electron. Base form the anion. Anion can mobilize. Conjugated systems are stable. So anion formed a terminal. You end up with final product. For clarity, it written as many steps. You can write it as single step. The concept you outline here is regioselectivity, very much important in organic conversion reaction. Then the next reaction, cyclohexane you have, side chain you have 2 methyl group and alcohol. You are using acidic condition. You should find what will be the final product. Here alcohol is there, acidic condition you are using. Alcohol removes the water, you form cation. Cation near the ring always expand. So 6-member ring becomes 7-member ring. You have tertiary cation. This rearrangement is promoted by cation stability. Secondary cation becomes tertiary cation. At the same time, 6-member becomes 7-member. It's a typical Wagner-Merwin rearrangement. Cation stability promoted rearrangement. Then cation is there, it has to be quenched. It can be quenched by hydrogen elimination. Again you have two possibility which hydrogen will eliminate, A or B. A hydrogen removed to the more substituted product, which is Sesef rule. B hydrogen leads to the minor substituted product. So major product is A removal. The concept you outline here is in Wagner-Merwin rearrangement, always cation stability promotes the reaction, while quenching cation follows Sesef product. Then the next example, you have cyclohexanone and you have 3 acidic groups. You are heating it up. You should find what will be the final product. Here problem in the plain side. So we have to redraw the molecule. We have to redraw the molecule for CO2 elimination. For that we have to promote the 6-member intermediate. So we draw carbonyl with sp2 hybridization. If you draw it, you have middle hydrogen. It can form hydrogen bonding with oxygen. So CO2 can eliminate. CO2 elimination leads to the enol in the system. If you rearrange, you end up with ketone. It's a very unexpected and unusual reaction. This is promoted by hydrogen bonding and CO2 elimination. CO2 is the gas like nitrogen. Since it forms multiple bonds, it's a very good leaving group. The concept you have to learn here is whenever you have more acid in the system, you should think CO2 elimination. Then the next example, you have ketone, which is the bridged cyclic compound with two bridged methyl group and one another bridged methyl group. You are using hydroxylamine and acidic chloride. You should find what will be the final product. Here ketone is there. You are using the hydroxylamine. So oxime is the product. Oxime form away from the bridge because of steric repulsion. So the chances of Beckmann elimination. First step will be acetylation of alcohol. Then you might expect Beckmann rearrangement. Since the cation is very stable cation because it's a tertiary cation, CN elimination will be there. Tertiary cation forms, CN the side group forms. If you redraw nicely, you have bicyclic compound too. You have cyclic compound. Bicyclic compound become normal cyclic one with cation. Then the cation has to be quenched. Only one pathway. Fourth hydrogen removed. You have alkene there. The concept you have to learn here is whenever you have stable cation formation possibility, Beckmann rearrangement become Beckmann elimination reaction. Then the next example, you have pyridine. Second position, you have chlorine. You are using sodium ethoxide. You should find what will be the final product. Here ethoxide is there. Ethoxide can undergo nucleophilic addition to the pyridine ring. It can add, but there is a possibility it can add anywhere in the ring, but it adds with chlorine because it has stability of anion from electronegative nitrogen as well as leaving group possibility of chlorine. So anion form, it is stabilized. Other attacks all will be minor. So major will be nitrogen stabilized anion. Then charge has to be quenched. So pyridine regained to gain the aromaticity. Then you end up with pyridine with OET substitution. Basically look like simple substitution, but it is stabilized and promoted by nitrogen there. The concept you outline here is aromatic nucleophilic substitution reaction possible with pyridine. It involves addition elimination mechanism. Then the next example, you have cyclohexene, methyl and isopropene is attached. You have thiophenol as the ether. You are using dimethyl zinc and methylene diiodide. You should find what will be the final product. By looking at diiodide, you might realize it's a Simon-Smith reaction. Here diiodide and zinc can form organometallic carbon. It can attack by sulfur. You have new sulfur halide. It's basically a sulfur halide formation reaction. Then sulfur halide can attack the alkene through the 2,3 sigma-tropic rearrangement. It's an unusual rearrangement only happen due to halide stability. So sulfur halide migrates. It's a rearrangement reaction. You end up with alkene there. Here you might have noticed sulfur is below the plane, product also below the plane. Since sigma-tropic rearrangement happen in the same plane, concerted reaction. So product also sulfur below the plane. The concept you have to learn here is sulfur halide can promoted by zinc carbon organometallics. Then the next example, you have benzaldehyde. Meta position, you have alcohol substitution. You are using the det reagent and phosphine and benzoic acid. You should find what will be the final product. By looking at the det reagent, you might realize it's a Mitsunobu reaction. It's an inversion in configuration reaction, very important naming reaction. Det means diethyl azo dicarboxylate. Due to the simplicity, it is abbreviated as DET. Here DET can abstract the proton, act like a base. So from benzoic acid, it abstracts the proton, generate the nucleophile, then nucleophile attacks. Attack happen with inversion configuration. You end up with ester there. So starting metal is below the plain alcohol, product is inverted one. So the inversion is like SN2 reaction. The concept you outline here is Mitsunobu reaction is stereospecific. Always inversion in configuration happen. Then the next example, you have ketone, phenyl and chlorine is there. You are using the methoxide. You should find what will be the final product. Here ketone is there, alpha position halide mean you might have realized it's a Favorsky rearrangement. The rearrangement involves cyclopropanone intermediate. So first step will be nucleophile generation. Then nucleophile attacks the alpha chlorine. It forms cyclopropanone. Then methoxide open the ring. Why? Because 3-member ring is highly strainful. The nucleophilic addition generates the anion. Then the anion travels, you have ring opening. Ring opening leads to the ester formation. You start with ketone, end up with ester. Finally, quenching leads to the phenolic ester. The concept you outline here is whenever you have alpha haloketone, it is a Favorsky rearrangement. Then the next example, you have cyclohexanone, alpha position, you have methyl. You are using dimethylamine and butyl lithium and ethyl bromide. You should find what will be the final product. Here you have ketone, amine you are using, so enamine is possible. The reaction is technically called Stark enamine reaction. It is a regioselective reaction because 2 alpha hydrogen is there, 2 nucleophile is possible. Due to the steric reason as well as anion stability, methyl side hydrogen is not absorbed. Other side, which is A hydrogen, is absorbed. So A hydrogen absorbed, you have nucleophile. Then nucleophile attacks the carbon, you have new CC bond. Then if you do hydrolysis, you end up with ketone. Basically, the reaction is promote carbon-carbon bond formation. The concept you outline here is enamine can promote the nucleophile generation, which in turn generate the carbon-carbon condensation. Then the next reaction, you have decline. It has diene and ketone in the system. One methyl at connected carbon. You are using the acidic condition. You should find what will be the final product. Here by looking at conjugated ketone, you might realize it's a dienone phenol rearrangement. First step will be attack on O. H plus attacks, you have cation. Then the cation promote the methyl shift there because cation can travel to stabilize itself. Always tertiary cation forms. Then the tertiary cation quench itself by alkene formation because alkene formation associated with aromatic compound. Aromatic compounds are more stable and it is a highly stable form in the cyclic system. So you end up with phenolic compound. The concept you outline here is dienone phenol rearrangement promoted by cation stability and end up with highest stable aromaticity. Then the next reaction, you have linear compound which is having 2-terminal diketone. You are using potassium hydroxide. You should find what will be the final compound. Here you have 2 ketone, many alpha hydrogen. Since the compound is symmetrical, only 2 types A and B are there. But according to enolate formation, more substituted enolate will form. So enolate form at B carbon. Then it is a internal nucleophile. Here intra also possible, but possibility of inter is lesser than intra because there is no need of collision. Internally nucleophile and electrophile available nearby. So it attacks, it has ring formation. If you redraw nicely, it is a beautiful 5-member ring with ketone. Alpha position you have alcohol. If you remove the water, you end up with conjugated ketone. Here driving force is the conjugation. The concept you outline here is in enolate formation, more substituted enolate will form. Then the next example, here you have fused system, 6-member and 5-member ring. Side chain you are using the amine, sodium nitrate and HCl you are using at low temperature. You should find what will be the final product. Here you have amine, NaNO2 and HCl you are using. It's a diacetization reaction. It will convert NH2 into N2+. It's a salt. N2 is gas. It's a good leaving group. After leaving, it form cation. Cation near the 5-member strainful ring. So it opens. Cation converted into stable secondary cation because secondary is more stable than primary. Cation conversion as well as ring strain removal, two stable factor promote the reaction. You end up with decalene cation. Then water attacks, you end up with decanol. The concept you outline here is whenever you have cation formation, strain in the system will be relieved. Then the next example, you have cyclohexane, diketone and acid in the same compound. You are reacting with light and water and heating it up. You should find what will be the final product. Here N2 is the lighting condition you are using. It's a Wolff rearrangement. Basically it's a carbene formation. N2 also a good leaving group. Losing of two bonds leads to the carbene there. Carbene is highly unstable. So what really happens is carbon migrates. You have cumulated carbonyl. Then water attacks. You have acid there. Then acid with alpha ketone mean it form hydrogen bond. CO2 removal leads to the enol. Finally, enol converted into ketone by tautomerism. You start up with 6-member ring, end up with 5-member cyclic ketone. The concept you outline here is the Wolff rearrangement involves carbene formation. Then the next example, here you have quinoline, 2 chlorines in the ring. You are reacting with diethyl aniline, ethyl alcohol and heating it up. You should find what will be the final product. Here you have amine, which is the nucleophile, and you have 2 chlorine in the system. So chances of aromatic nucleophilic substitution reaction. It is a addition elimination reaction. Here amine can attack 2 chlorine, but amine will attack only the 2nd chlorine because it will form stable anion with nitrogen. The charge travel, nitrogen anion forms, then anion has to be quenched. So the charge travel again, chlorine elimination, you end up with biphenyl kind of compound. So both ring gains the aromaticity by this process. You end up with final product. The concept you outline here is whenever you have halogen in the benzene, aromatic nucleophilic substitution is possible. Then the next example, here you have fused and spiro system, benzene and 5-member lactone, spiro system in dimethyl ketone. You are using acidic condition. You should find what will be the final product. Here by looking at dienone in acidic condition, you might realize it's a dienone phenol rearrangement. The rearrangement is driven by the cation stability. First step will be attack of H+. It will form alcohol. Then cation travels. You have cation near the oxygen. The cation is stable because it is a tertiary kind of cation. Then 5-member ring is strainful, open itself. You have 6-member ring formation. Then hydrogen elimination is possible. You finally end up with aromatic compound. Whole reaction is driven by aromaticity of the phenol. So charge travel, ring expands. Finally you end up with aromatic compound. The concept you outline here is dienone phenol rearrangement promoted by cation stability as well as aromaticity. Then the next reaction, you have naphthalene connected with ethylene. You are using N-bromosuccinamide 2 equivalents, light and carbon tetrachloride you are using. You should find what will be the final compound. Here N-bromosuccinamide you are using, it's a brominating compound, bromine donor. But where the bromine attacks is the real question. The ring substitution needs Lewis acid. Here no Lewis acid. So only side chain substitution. So side chain bromine is substituted. It's allylic substitution or benzylic substitution. You have bromine there. Second equivalent where it will attack whether bromine at the same carbon or different carbon, that is vicinal or geminal. Vicinal is possible because of steric free reason. Bromine is bulky, so try to stay away from each other. So finally you end up with 1,2-dibromo compound. The concept you have to learn here is ring substitution of benzene needs Lewis acid for the activation. Then the next example, you have cyclopropane. One side you have alcohol, another side you have ketone. You are using sodium hydroxide, acidic hydrolysis. You should find what will be the final product. Here you have alcohol. You are using the base. Base abstract the proton, form the nucleophile. Since the system is strainful, there can be a many possibilities. So charge travel end up with O- in the carbonyl. So the ring open, charge travels. You have enol. If you redraw nicely with tautomerism, you end up with diketone there. Since you are using the basic condition, you end up with the possibility of aldol reaction. So proton abstraction happen. Proton abstraction leads to the internal nucleophilic addition reaction. So generated nucleophile attacks the carbonyl. You have new ring formation. If you redraw nicely, it's a 5-member ring with ketone, hydrogen and alcohol nearby. If you remove it, you have conjugated ketone. The concept you have to learn here is you have to always imagine the reaction and continue the reaction with the functional group availability. Then the next reaction, you have cyclohexanone. Alpha position you have N2 group. You are using light and methyl alcohol. You should find what will be the final product. Here light and azo group is there mean chances of Wolff reaction. So Wolff rearrangement reaction. Basically light promote the N2 elimination because N2 is a good leaving group. It is a gas. Sudden leaving of two bonds leads to the carbene. Carbene is highly unstable. So another alpha carbon migrates, stabilize itself, form a cumulative ketone. It is with continuous double bond. Then methanol attacks. You have ester there. The concept you have to learn here is Wolff rearrangement always occur with carbene formation. Then the next example, you have alkene, third position you have alcohol and terminally you have dimethyl group. You are using SOCl2. You should find what will be the final product. Here you are using SOCl2. Immediately you think of the chlorination, which is substitution reaction. But it is not possible because SOCl2 attack in the system leads to the OS bond formation. Then rearrangement occur with the chlorine formation. So you have terminal chlorination, not the third position chlorination. It's a kind of minor rearrangement with the sulfur chloride. Then the next example, you have cyclohexane and butane. You are having hydroxylamine, phenyl and hydrogens are syn to each other. You are using the sulfuric acid. You should find what will be the final product. Here by looking at the oxime in acidic condition, you might realize Bachmann rearrangement reaction. First step will be OH removal. OH removes the water. The trans group migrates because the reaction is stereospecific. Trans group migrate. It assists the water elimination and it forms cation in the carbon. Then if you redraw nicely, you have cation in the 5-member ring. Water attacks. It's a kind of enol. You convert it into ketone. So you start from oxime, end up with amide there. The concept you have to learn here is Bachmann rearrangement migrating ability does not matter because always trans group migrates. Then the next reaction, you have pyridine. second position amide, third position acid, fourth position chlorine. You are using bromine and KOH as a reagent, aqueous NaNO2 and sulfuric acid. You should find what will be the final compound. Here you have amide, bromine and base you are using it. It's a Hoffman elimination. Basically it's a degradation reaction. One carbon less from the reactant end up with amine. Then NaNO2 you are using. It's a diacetization reaction. You convert NH2 into N2Cl. Further you are using aqueous condition. It leads to the alcohol. So you start up from amide, end up with alcohol. It's a completely functional group transformation. Further, if you notice clearly, three functional group which will reacts mean only amide reacts because of reagent. It is called chemoselectivity. Among the three, only amide reacts. The concept you have learned here is Hoffman elimination is a degradation reaction formed with one carbon less. Then the next example, you have benzene, aluminum chloride you are using, and you have alpha, beta unsaturated acid. You should find what will be the final product. Here aluminum chloride you are using. Aluminum can attack the carbonyl and activate it. You have activated carbon. The carbon activation formed with cation, but cation will be better stabilized if it is a tertiary cation. So tertiary cation form, it can attack aromatic compound, basically a aromatic electrophilic substitution reaction, new CC bond. Then if you do tautomerism, you end up with acid again. Finally, you have unexpected rearranged product. The concept you have learned here is regioselectivity. Whether acylation or alkylation happen is the real question. Here alkylation happened because of the cation stability. Then the next reaction. Here you have bicyclic compound with alkene and acid. You are using the sulfuric acid. You should find what will be the final product. Here acid you are using. Acid can form cation but regioselectively, but the selectivity decided by the next step, which is ring formation. Because acid is the attacking species, acid can approach the first position then the second position because of ring is rigid. All system is cyclic here, so attack is only possible from endo position as well as only on first position. You can say it's a combination of stereospecificity and stereoselectivity. Finally, end up with bicyclic system. The concept you outlined here is final product can also dictate the reaction pathway. Then the next reaction. Here you have fused compound, 7 member and 5 member ring. You have ketone, alcohol and 2 methyl group. All are stereochemically specified. You are using sodium hydroxide, carbon disulfide and methyl iodide. High temperature, which is 200 degrees Celsius. You should find what will be the final product. By looking at the carbon disulfide and alcohol, you might realize it's a Chukov elimination reaction. Chukov elimination is the abstraction of alpha proton through the carbon disulfide reaction. First step will be nucleophilic addition on carbonyl, then sulfur near the hydrogen is there. If you redraw nicely, you can bring hydrogen and sulfur nearby. You have alkene formation by the elimination. Since the mechanism is concerted, alkene is the cis alkene. It's a pyrolytic syn elimination reaction. Technically, the mechanism is EI mechanism. It's an internal elimination reaction mechanism through the 6-member transition state. Here, heat is the primary driver which promote the elimination. The concept you outlined here is Chukov elimination is the pyrolytic syn elimination. Cis product will form. Then the next reaction. The starting metal is cyclohexene. Side chain you have acid. You have bromine and solvent. You should find what will be the final product. Here you have alkene. You are using the bromine mean brominium ion formation. Bromine with cation. It is a very strainful compound. So it can be attacked by the acid, which is a nucleophile in the system, but it can attack two-way, which is first carbon and second carbon. Another is above the plane and below the plane. Since the mechanism is SN2 reaction, the attack is from below. It is a stereoselectivity, and it attacks the first carbon. It is a regioselectivity. So stereoselectivity as well as regioselectivity in the same reaction. Finally, you end up with syn ester, which is syn lactone. The concept you outline here is you should master stereoselectivity and stereospecificity. Then the next reaction. Here you have cyclohexanone, bromine and acetic acid you are using. Sodium methoxide as the reagent. You should find what will be the final product. Here you have ketone, base you are using, abstraction of acidic proton which can generate the nucleophile. The nucleophile attacks the bromine. You have bromine bond. You have bromine bond. So alpha halohetomine favors key rearrangement. Acidic proton abstraction. It can generate the nucleophile which attacks the bromine. You have cyclopropanone. The cyclopropanone is unstable. It's a strainful compound. Methoxide attacks. You have ring opening with ester formation. The ring strain promote the ring opening. You have ring contraction because you start from 6 member, you end up with 5 member. The concept you outline here is whenever you have alpha haloketone, you should imagine Favorsky rearrangement. Then the next reaction, you have cyclic ether, you are converting into cyclobutane. You should find the reagents and number of steps involved in the conversion reaction. Here you have cyclic ether, so you have to convert into 4-member mean. You should remove the oxygen. So the first step can be attack of hydrogen iodide, form alcohol and iodine because ring open. You have one side iodide, another side alcohol. Again same hydrogen iodide you are using mean alcohol again convert into iodide. So 2 iodide in the system. If you use Wood's reaction, sodium as the reagent mean you have cyclobutane. It's a simple conversion with simple reaction steps. The concept you have to learn here is to master the organic conversion, you should master the reagents. Then the next reaction, you have fused system, cyclopentene and cyclobutanone. Both are connected in syn way because hydrogens are syn to each other. You are using hydrogen peroxide and acetic acid. You should find what will be the final product. Here ketone you are using hydrogen peroxide as the reagent. So epoxide formation. Here two possibility. It can attack alkene. It can attack carbonyl. Alkene is the neutral species. Carbonyl is the activated one because of carbonyl positive charge. Acidic condition also promoted. So instead of epoxide formation, it form major nucleophilic attack on carbonyl. So you have the possibility of pair villager rearrangement. The ring opened by the methylene group migration. Normally electron rich group migrates because intermediate is electron deficient. So carbon migrates, you have the cation. The cation is near the alcohol. So cation convert into carbonyl by the H plus elimination. The concept you outline here is among the reactivity of carbonyl and alkene, carbonyl is reactive because of its polarity. Then the next example, here you have bridged compound and you have ketone and bridge methyl group. You are using the hydrogen in tosylate form. Methyl lithium you are using. You should find what will be the final product. Here by looking at the hydrazine and carbonyl, you might realize it's a Sapphiro elimination reaction. Basically you are converting ketone into alkene. The steps are interesting because you have hydrazine and carbonyl. It form hydrazine. Then methyl lithium you are using. Lithium promote the acidic hydrogen, form the anion. Then you have further acidic proton removal which needs to another anion. it travels. Remove the N2 as well as TS elimination. N2 is the good leaving group. TS, which is tosylate, also good leaving group. Finally, you have anion with alkene. Then it is conjugated with removed H+. Finally, you end up with alkene there. Basically, it's a functional group conversion of carbonyl to alkene. The concept you outlined here is mechanism of sapphire elimination is critical. It is driven by nitrogen and tosylate elimination. Then the next reaction. Here you have diester with linear chain compound. You are using sodium hydroxide. You should find what will be the final product. The reaction is Dickman condensation, basically a modified version of aldol reaction. So the first step will be abstraction of proton. Acidic proton remove, you have nucleophile. Nucleophile can act intramolecular way or intermolecular way. Intra is possible because of no collision. So nucleophile attacks carbonyl. ETO is the leaving group. You have new cyclic compound. Basically a condensation reaction happen in a single molecule. You have cyclic product. The concept you outline here is Dickman condensation can happen intramolecular way if you have diester in the same compound. Then the next example. Here you have adamantane system. It is the ketone. You are using sodium nitrate and trifluoroacidic acid. You should find what will be the final product. Here you have ketone and acid. You might realize it's a Smith rearrangement. Basically, the first step will be nucleophilic addition. Acid is the nucleophile. It attacks, it forms carbon-nitrogen bond. Then N2 is the good leaving group. Ring open. Since the migrating groups are symmetrical, migrating ability does not matter. Ring carbon migrates. You have N2 elimination. Finally, you end up with amide. So you starting from ketone, you end up with amide with ring expansion. The concept you outline here is in symmetrical system, migrating ability does not matter. Then the next example, you have benzene, nitro and ketone with meta relation. You are using sodium borohydride and tin and HCl. You should find how the reagent behave differently with same reactant. The reaction is the chemoselective reaction. Sodium borohydride attacks the carbonyl, not the nitro compound. Here nitro compound cannot be reduced because H- cannot attack the nitrogen. Due to its saturated valency, nitrogen already 4 member occupied, so it cannot attack. Only possible is carbonyl. You end up with alcohol. On the contrary, tin and HCl you are using mean tin reduction is the heterogeneous reaction because tin is metal. It stay out of solution. So only charges interact. In homogeneous reduction of carbonyl is possible. Since it is heterogeneous, NO2 is polar. It can bind easily with tin. So the reduction happen at nitro, not with amine. It's an important chemoselective reaction. Sodium borohydride only reduce the carbonyl. Tin and HCl only reduce the nitrate. Then the next example, here you have decline, one with conjugated ketone, another with simple ketone. You are using sodium borohydride. You should find what will be the final product. Here basically H- is the nucleophile. Where it will attack is the real question. Whether it attacks A carbonyl or B carbonyl. A is the simple carbonyl system. B is the conjugated carbonyl system. Before going to that, there are 4 possibilities P, Q, R, S. To identify this, you should know the reagent as well as reactant. Sodium borohydride is the weak reducing agent because boron and hydrogen bond is stronger. It cannot donate H- easily. If you look at B carbonyl charge is not static, charge is on delocalization. It's a dynamic system. On the contrary, on the A, charge is static, not dynamic. And alkene also cannot reduce by H- because same charges repel each other. So only possibility is A carbonyl reduction. It reduces, you have the final product. This reaction is very much important in terms of selectivity. Why? Because we're eliminating all the possibilities by the basic chemistry. Whole regioselectivity or chemoselectivity can be analyzed by the fundamentals. Here you have cyclohexane attached with COCH3. You are using the peracid. You should find what will be the final product. Here you are using the peracid attacks the carbonyl. You have new CO bond. Here OO bond is weaker. That is what promote the Bayer-Villiger oxidation. It's a rearrangement reaction. Basically the intermediate is cation. So tertiary group migrates better than primary. So ring carbon migrates. You have cation near the alcohol. If you redraw nicely, you have cation near the alcohol which form ketone there. The concept you outline here is in Bayer-Villiger oxidation, tertiary carbon migrates. Then the next reaction, here you have ether, both position attached with ester. You are using KOH acidic condition, heating it up. You should find what will be the final product. Here you have diketone, basic condition you are using. So the possibility of Dickman condensation, it's a kind of aldol reaction but happen in the ester. So first step will be abstraction of proton. It form nucleophile. Nucleophile can attack internal electrophile. It attacks, you have OMe elimination and cyclization reaction. Here intramolecular reaction is more possible than inter because no collision of molecules required. Further, acidic condition you are using, it converts ester into alcohol. You end up with alpha hetoacid. Alpha hetoacids are unstable because hydrogen bonding leads to the CO2 removal, end up with enol. So enol can be rewritten as carbonyl. So you start from linear compound, end up with cyclic ketone. So it's an important conversion reaction. The concept you outline here is alpha hetoacids are unstable. It will convert into ketone by cyclization reaction. Then the next reaction, you have cyclobutane. You are reacting with bromine. You should find what will be the final product. The reaction may look simple, but it involves deep mechanism. Whether cis product or trans product form is the real question. First step will be attack of bromine on alkyne. It leads to the brominium ion kind of intermediate. Next step, bromine attack. It's a kind of SN2 backside attack which leads to the ring opening. Since bromine are bulky, only backside attack is possible, which leads to the trans product. In more simple term, bromine addition is the anti-addition, end up with trans product. The concept you outline here is in alkyne system also bromine addition is anti-addition. You end up with trans product. Then the next reaction, you have linear compound which contain alkene and alcohol. You are reacting with HBr, copper cyanide and concentrated HCl. You should find what will be the final product. Here you have alkene and alcohol. HBr you are using mean Markovnik of addition to the reaction. Here alkene and alcohol is there. You are using the acid. It can be a two possibility, alkene addition reaction or water removal. Among the alkene and alcohol, alcohol is more reactive because of polarity. So OH2 plus formation. So it can be converted into cyanide by cyanide attack. Then acidic hydrolysis leads to the acid there. The reaction is very much interesting because you are having competing mechanism, addition and substitution. Substitution dominated by the polarity of OH. Then the next reaction, you have cyclohexanone. Side chain you have ketone. Reacting with potassium hydroxide. You should find what will be the final product. Here you have many possibility, many alpha hydrogen which will be removed. that is regioselectivity. Here C hydrogen is removed because A hydrogen cannot attack another carbonate because of ring rigidity. B hydrogen leads to the small ring size product that is also minor. So only possibility is C proton abstraction, which form nucleophile minus charge. It attacks, you have cyclic compound. Then if you redraw nicely, you have 6-member fused decline compound which has the possibility of water elimination because hydrogen and OH is nearby. Hydrogen is acidic. It forms conjugated ketone. Driving force for this step is conjugation reaction. The concept you have to learn here is if you have many possibility on hydrogen, always choose the product based hydrogen abstraction. Then the next example, you have fused compound which is two pentane fused together which has hydroxylamine as the functional group. You are using sulfuric acid. You should find what will be the final product. Here you have hydroxylamine. Acidic condition you are using in Beckmann rearrangement reaction. Basically first step will be water removal. H plus makes OH as a water good leaving group, but it need assistance from the trans-methyl group. Here migrating ability of Beckmann rearrangement always with trans group, it is stereospecific. So trans group migrates, water eliminates. You have cation on the carbon. If you redraw nicely, you have 5-member compound become 6-member compound with cation. Then OH minus attacks, you have enol there. Then the enol converted into ketone, which is amide there. The concept you have to learn here is in Beckmann rearrangement, always trans group migrate. Then the next reaction, here you have linear chain cyanide. You are using the base. You should find what will be the final product. The reaction is called Thorpe condensation. It's a kind of self-condensation. First step will be alpha hydrogen removal. Why? Because cyanide is the electron withdrawing group. It can stabilize the generated nucleophile or anion. So it is a better one. It attacks itself. The carbonyl carbon is attacked. You have new CC bond. Then nitrogen hold the negative charge. Then it abstract the hydrogen. It become imine there. Then the tautomerism happen. You have NH2, NH2. The concept you have to learn here is in Thorpe condensation, cyanide can generate the alpha nucleophile, attack itself, form the condensation reaction. Then the next reaction, you have linear chain compound. In both terminal, you have ester. You are using sodium ethoxide and methyl iodide. You should find what will be the final product. The problem in the plain side, if you redraw nicely for the cyclization, you might realize it's a Dickmann condensation. If you redraw to the cyclohexane format, you can understand it can undergo Dickmann condensation. First step will be proton removal. Acidic proton remove, you have nucleophile there. Nucleophile can attack itself. Instead of going intermolecular, it will go intramolecular because there is no collision required. So anion attacks, you have OET leaving group, you have 5-member ring formation. Then again base you are using, base abstract the proton, methyl iodide is there. The generated anion act like a nucleophile which attacks, you have new CC bond. The concept you have to learn here is long chain diester compound can undergo Dickmann condensation. Then the next reaction, you have linear chain compound, amine is there, both side alkyl group, third position is chlorine. You are using sulfuric acid and heating it up. You should find what will be the final product. The reaction is called Hofmann-Loeffler-Frittag reaction, basically a kind of rearrangement reaction. First step will be quaternary ammonium salt formation. So amine attacks the proton, it forms quaternary ion. Then heating it up, you are generating radical cation. Then it can abstract the delta hydrogen. It is the main condition for the naming reaction. So it abstracted, you have radical transfer. Then the radical absorbed back by chlorine. Then amine is there, which is internal nucleophile. Chlorine is the good leaving group. So attack happened. You have cyclopentane ring with heterocyclic nitrogen. The concept you have to learn here is Hofmann-Loeffler-Prittak reaction. Delta hydrogen is critical. It involved rearrangement reaction. Then the next reaction. Here you have benzene. Side chain you have diester. You are using the base acid hydrolysis. You should find what will be the final product. The reaction is Dickmann condensation. First step will be abstraction of proton by the base. It forms nucleophile. Nucleophile can undergo intermolecular as well as intramolecular, but intermolecular possibility is less. Why? Because there is no collision required for intra, so the possibility attack is more. So intra is favorable than inter. So it attacks. You have OET elimination and new CC bond with 5-member fused ring formation. The reactant react itself. It's a kind of self-condensation reaction. Finally, you end up with ketoester. The concept you have to learn here is the Dickmann condensation happen in the diester system. Always form cyclic product. Then the next reaction, you have acetaldehyde, alpha haloester. You are using the base. You should find what will be the final product. The reaction is called Tarzan reaction. First step will be removal of acidic proton. Here 2 carbonyl is there. Alpha haloester proton is subtracted because 2-side electron withdrawing group leads to the proton more acidic. It forms nucleophile. Then it attacks. You have new CC bond with O minus. O minus is nucleophile. It can attack bromine. Bromine is the leaving group. You form epoxide. This reaction end up with unusual product. That's why it gain its own popularity. The concept you have to learn here is Tarzan reaction happen with alpha haloester. Then the next reaction. Here you have cyclohexane with dihetoform. You are using the base. You should find what will be the final product. Here you have diketone and base. The possibility of benzylic acid rearrangement. First step will be attack of OH minus. Since the system is symmetrical, it can attack anywhere. The product will be same. Then the charge has to quant. So O minus travel, carbon migrates. You have O minus with acid, then O minus quenched with hydrogen plus. You end up with alcohol and acid in the same carbon. If you redraw nicely, you end up with ring contraction. 6-member ring become 5-member with acid and alcohol. Here you may observe the weird thing because charge quenching happened. 6-member will become 5-member, which is strainful ring. Why? Because charge quenching has higher priority than ring strain. That's why ring contraction happened. Then the next reaction, you have benzene with acid chloride at the side chain. You are using sodium azide, acidic hydrolysis and heating it up. You should find what will be the final product. By looking at the azide, you might realize it's a courteous rearrangement reaction. First step will be attack of the nucleophile on the electrophilic carbon. Cl leaves, N3 form. You have acyl acide. If you redraw nicely for the rearrangement, N2 is the good leaving group. It's a gas with triple bond. Form quickly. The group migrates. You have cumulative double bond. Here NCO is isocyanate. It forms. Then hydrolysis bring the acid there. If you are heating it up, it converts into amine there. Finally, you end up with aniline. The concept you have to learn here is whenever you see acid in the heating condition, you should imagine courteous rearrangement reaction. Then the next reaction. Here you have benzaldehyde, phosphenylide you are using, then conducting acidic hydrolysis. You should find what will be the final product. By looking at the E line, you might realize it's a Wittig olefination reaction. First step will be attack of nucleophile, the nucleophilic addition on carbon. It forms new CC bond with phosphine positive charge, oxygen negative charge. Phosphorus oxygen bonds are stronger, so it forms quickly. Once it forms, the phosphine elimination is possible as a phosphine oxide. Then you end up with alkene. If you do hydrolysis, ester become alcohol, then it is the enol. Finally, you end up with aldehyde there. You start from aldehyde, but one CH2 is inserted through Wittig reaction. The concept you have to learn here is aldehyde and aldehyde will undergo Wittig reaction. Then the next reaction, here you have ketone, both sides you have alkene, one is propene, another is isopropene, you are using sulfuric acid. You should find what will be the final product. Here you have carbonyl, you are using acidic condition, so carbonyl is activated, you have cationic carbon, then rearrangement possibility is there, charge migrates, form the enol there. Then the cation has to be quenched. Cation quenched as alkene there. Here conjugation drives the final step in with alpha, beta unsaturated ketone. Here starting middle is the enone. Final product is cyclic conjugated ketone. Then the next reaction, benzene attached with amine and carbonyl. Then the compound is switched. Carbonyl is attached with benzene. Again it's amine. Both cases we are reacting with sulfuric acid and nitric acid. You should find what will be the final product. Here the question is purely regioselectivity, how the functional group influence the incoming group. In the compound A, amine is attached with benzene. Amine is electron rich, mesomeric, donate the electron to the ring. So ring will become richer. So it become ortho-para director. Ortho is steric, so para is formed. On the contrary, carbonyl is sp2 carbon, electron withdrawing because S character is high. So only meta position is possible. You end up with meta nitration. The concept you have to learn here is you should watch the attachment of the atom to conduct the best possible organic conversion. Then the next reaction, starting middle is benzene with amine, side chain alpha keto acid. You have two different conversion. One is 5-member ring formation, another is 6-member ring formation. Basically amine and ketone interaction. You should find reagents and number of steps involved in the organic conversion. Here if you simply heat it up, amine and carbonyl condense, you have 5-member product. First step will be amine attacks carbonyl. It will form alcohol. Alcohol and hydrogen at the nearby carbon means you end up with imine. Then if you do sodium cyanoborohydrate, which is selectively for imine, it's a chemoselective reagent, then you get the final product. If you go to the another pathway, first you got to protect the ketone because ketone is very reactive than acid. If you protect it with diol, you have acid. Acid and amide both will react. It's acid-base reaction. Water eliminates, you end up with amide there. Then if you use lithium aluminum hydride, carbonyl is selectively reduced. Then you can deproduct it by hydrolysis. So one case you end up with 5-member, another case you end up with 6-member. The concept you have to learn here is you should know chemoselective reagents and productive reagent to master the organic conversion. Then the next reaction, you have benzene and cyclohexanone in the fused form and you have O-methyl as the functional group. You are using sodium ammonia and ethyl alcohol. You should find what will be the final product. Here you are using sodium and ammonia, basically a Birch reduction because benzene ring is there. Ammonia and sodium you are using in Birch reduction. First step will be diradical formation. Then diradical converts into anion. Here many possibility of anion formation. One will be anion near methoxy group. Both will repel. Why? Because oxygen has lone pair which is also electron rich. Electron repulsion happen. On the contrary, if it happen at the middle carbon, there is no extra special stability. So only possibility is C. So A and B not form, only C form. Finally quenched with hydrogen, you end up with final product. The concept you have to learn here is Birch reduction reaction totally controlled by anion stability. Then the next reaction, you have benzene side chain O-methyl group fused with 5-member heterocyclic ring. You are using sodium and ammonia and ethyl alcohol. You should find what will be the final product. This reaction is similar to the previous one. First step will be radical formation. Since the diradical forms, it happen at para position. Diradical convert into anion, dianion. Further, it is quenched by hydrogen. You end up with final product. Let us analyze other two possibility. If anion form near oxygen means lone pair repulse, it won't form. Other case also same, anion repelled by O-methyl group. So repulsion don't allow the reduction reaction. Finally, you end up with proposed mechanism. The concept we outline here is which reduction controlled by anion stability. Then the next example. Starting middle is benzaldehyde. Para position you have bromine. One side you are converting aldehyde into alcohol. Other side you are converting bromine into alcohol. Two different conversions. You should find what are the steps, reagents involved in the conversion reaction. Here conversion of aldehyde into alcohol is easy. Just use Regnard reagent. It converts into alcohol. On the contrary, converting bromine is harder because carbonyl is very reactive and polar. So first we have to protect it. We protect it with diol. Carbonyl is protected and dampened. So you can convert bromine into magnesium bromide. Then attack with aldehyde. You end up with alcohol. Further, if you do deprotection, you end up with aldehyde, that is desired product. The concept you have to learn here is you can play with reagents to get the desired organic conversions. Then the next example, here you have decline with ketone and alkene. You are using two different reducing agents. One is hydrogen and ranite nickel, another is sodium borohydride. You should find what difference the reagents can make. Both reaction is about chemoselectivity, which functional group reacts. Here sodium borohydride if you are using it, you are attacking with H-. H- is already negative charge. Alkene it cannot attack because pi electron is electron cloud. So only aldehyde attacks, you end up with alcohol. Alkene is not reacted. On the contrary, if you use metallic reduction, metal can activate the alkene as well as carbonate. So you end up with both the reduction. Here selectivity achieved by sodium borohydride, but ranite nickel and hydrogen reduce both of them. The concept you outline here is you should master the chemoselectivity to master the organic conversion reaction. Then the next reaction, you have alkyne both sides with methyl group. You are reacting with palladium, hydrogen and barium sulfide. You should find what will be the final product. Here you have alkyne. You are reacting with palladium, hydrogen and barium sulfide. It's a Lindlar's catalyst. It converts alkyne into alkene but in the cis fashion. Why? Because palladium is the metal, it can coordinate with alkyne on the same phase. So only syn kind of reduction is possible. Since it attached to palladium surface, only attack from hydrogen on the same phase is possible. So only cis is the major product. It's a stereoselective reaction. Cis is major, trans is minor here. The concept you outline here is alkyne can be selectively reduced to cis fashion by the Lindlar's catalyst. Then the next example, you have propene reacting with mercuric acetate, water, sodium borohydride and borane with hydrogen peroxide and base. You should find how the reagents behave differently with same reactant. The reaction is about regioselectivity, where the reagents attacks, where the product forms. Product is alcohol. With mercury, it forms two alcohol. Markovnikov rule. OH at the substituted position, which is more substituted carbon, because mercury forms mercurium ion and ring opening, which leads to the stable cation intermediate. That's why Markovnikov product. It's a mercuration and demercuration reaction without cation formation. On the contrary, borane forms anti-Markovnikov rule because boron is the attacking species and electrophile. end up with terminal hydroxylation. If you want to study the mechanism, study separately, but both reactions are important and very good regioselectivity exercise. Then the next reaction, you have quinone. One side you have methyl group, another side you have methoxy group. You are reacting with 180 degrees Celsius and butadiene. You should find what will be the final product. Here you have diene and dienophile situation. Obviously Diels-Alder reaction. Dienophile should be electron deficient. If you compare methyl and methoxide, methyl can be less electron deficient because strength of mesomeric effect is higher than inductive. Methyl is inductive, methoxide is mesomeric. So electron density of B is lesser than A. B reacts. You have major product with B dienophile. So you have 4 plus 2 cycloaddition happen. You end up with syn hydrogen because addition is syn addition, same plane addition. You end up with cis methyl and hydrogen. The concept to outline here is dienophile should be electron deficient, diene should be electron rich for the Diels-Alder reaction. Then the next example, you have linear chain compound with ketone and one methyl group which is stereochemically above the plane. Sodium borohydride, methoxide you are using. Acidic hydrolysis at the next step. You should find what will be the final product. By looking at ketone and stereochemistry, you might realize it's a Gram's rule. For that you have to separate large, small and medium group. So we redraw with specification. Large, small and medium. Large group is propyl group. H minus attack the medium side according to Gram's rule. If large group and CO is anti-mean, small side attack. Sin mean it's a medium side attack. Large side never the attack happened. So the attack happened on the medium side. Medium side is methyl. So H attacks from methyl side which is above the plane, which is very important organic conversion reaction because you are playing with stereochemistry and rule. Very important thing. The concept you outline here is in Gram's rule, large group anti to CO mean small side attack, syn to CO mean medium side attack. Then the next example, you have cyclohexanone, two side methyl group. You are reacting with potassium hydroxide and pH2S2 sodium iodide and heating it up. You should find what will be the final product. The answer lies in the basics. First step you are using the base. The starting metal has alpha hydrogen. It abstracts the proton, form the nucleophile. Then you are using disulfide. You can imagine it like peroxide analog. So nucleophile attacks, you have pH sulfur bond. Then you are using iodide. Iodide converts sulfur into sulfoxide. It is basically a oxidation of sulfur. Then if you have alpha hydrogen, sulfoxide elimination happen. You end up with alkene there. So you start from ketone, end up with conjugated ketone. The concept you outline here is sulfoxide elimination. If you have active hydrogen and you have sulfur as the reactant, you may end up with conjugated ketone. Then the next reaction, you have methyl allyl alcohol. You are reacting with HBr, copper cyanide and concentrated HCl. You should find what will be the final product. Here first step will be HBr reaction. HBr can be acid, HBr can be a nucleophile. That is, question is about whether the reaction is addition or substitution. The reaction has the possibility that HBr can act as an acid because alcohol is more polar than alkene. It reacts first. So OH2 plus form, not the HBr addition. OH2 is the good living group. So cyanide attacks. The mechanism is SN2 prime mechanism, meaning it attack on the terminal, double bond switches. You end up with cyanide at the terminal position, alkene at the third position. Then the acidic hydrolysis you are using, you end up with acid. The concept you outlined here is polarity of compound can dictate the reactivity. Most of the time, more polar compound reacts. Then the next reaction, you have pyridine and aldehyde. You are reacting with active methylene group and base, then dimethylamine, lithium aluminum hydride. boron trifluoride with aldehyde, many reagents. You should find what will be the final product. Here first step active methylene compound which is diester. So attack on carbonyl will be the Novo-Nagel reaction. So it attacks the carbonyl. You have new CC bond and end up with alcohol. Then amine you are using. Alcohol converts into amine. If you redraw nicely, you have the possibility of cyclization because diester can be reduced by lithium aluminum hydride. Ester become alcohol. Alcohol can form cyclization with aldehyde. So diol with aldehyde means kind of protection reaction. Acetal forms. So you end up with cyclic compound. The concept you outline here is you should have command and the basics because unexpected turns, unexpected twist will come in organic conversions. Then the next reaction, you have cyclohexenol reacting with zinc copper couple and methylene iodide. You should find what will be the final product. By looking at diiodide and zinc copper couple, you might realize it's a Simon-Smith reaction. First step will be formation of methylene group. It can be simply written as attack on the below side or above side. Above side will be major, below side will be minor. The reason can be easily understood by redraw in the chair form. If you draw the chair form, you have zinc attack. Zinc can coordinate with oxygen, so it can form on the same phase. So methylation happen with same phase of oxygen. So methylene and alcohol in the same plane. That's why you have syn-methylene alcohol relation. You can draw either above the plane both or either below the plane. The concept you got to learn here is Simon-Smith reaction can be coordinated by mesomeric groups. So the product will be syn product. Then the next example, you have linear compound with triene. It's written with bent bond angle. For the cyclization reaction, you are heating up for 180 degrees Celsius. You should find what will be the final product. Here by looking at the reactant, you might realize it's a pericyclic reaction. It's a thermal reaction with 6 pi electron. 6 pi mean 4n plus 2 system with n equals 1. So thermal 4n plus 2 mean disrotation. Here terminal 2 alkenes are trans and disrotation mean you use the table to find the product which is trans in disrotation mean always syn product. So the concept you outline here is pericyclic reaction. You should find number of pi electron and geometry of terminal alkene. With this table, you can identify what could be the final product. Then the next reaction, you have conjugated ketone. It attached with cyclohexane. You are reacting with HCN and KCN. You should find what will be the final product. The question is really about the addition is 1,2 addition or 1,4 addition. 1,2 addition mean addition on carbonyl. 1,4 addition mean addition on terminal 4 alkene. So the concept will be Michael addition. Soft nucleophile undergo 1,4 addition which is Michael addition. Cyanide is the soft nucleophile because charge is distributed and big. So it will only attack on 4th carbon. So attack happened. You have charge travel. Then O minus form. It will be quenched with H plus. End up with enol. Enol can be tautomerized to ketone. You end up with final desired product. The concept you outline here is cyanide is the soft nucleophile. Always undergo 1,4 Michael addition. Then the next example, you have benzene fused with 5-member system. Side chain you have ester, actually a diester. You are reacting with butyl lithium and methyl iodide. You should find what will be the final product. Here the concept called ortholithiation. It's a regioselective proton abstraction. Only orthoproton is abstracted due to lithium intermediate. The coordinating species and lithium can form transition state which can stabilize the lithium with hydrogen. So hydrogen can be easily abstracted. Other hydrogen don't have such an advantage. So ortho position hydrogen is weakened, form as a nucleophile. then you are reacting with methyl iodide. Nucleophile attacks, you have new CC bond. Basically, you are guiding incoming methyl group to the ortho position. That's why it's called ortholithiation. The concept you outlined here is ortholithiation. It's a directive methylation reaction and regioselective. Only ortho position is occupied, not meta and para. Then the next reaction, you have conjugated diene attached with O-methyl group and siloxane. You are heating it up using acidic condition and vinyl cyanide you are using. You should find what will be the final product. By looking at the diene and dienophile, you might realize it's a Diels-Alder reaction. The question is what kind of product forms because different regioselectivity is possible. According to Diels-Alder orbital overlap, only ortho and para-like product form, not meta-like. So only possibility is B, not the A compound, because A compound is meta, B is ortho, para is not possible. So P is formed. Then you are using acidic hydrogen. It abstracts the methyl group. It converts O-methyl into alcohol. Finally, you have functional group conversion. Then acidic condition you are using. It will convert OH into OH2 plus. Trimethyl silide is a good leaving group, so try to leave itself, form a conjugated ketone. So completely unusual product. The concept you outlined here is in Diels-Alder reaction, ortho and para-like product form, not the meta-like product. It's a regioselective addition reaction. Then the next reaction, you have cyclohexenone with methyl and isopropene. You are reacting with sulfoxyhalide and sulfur halide, two different reagents. You should find what difference it can make in the reactant. The reaction is all about regioselectivity by the nucleophilicity. Everybody knows soft nucleophile undergo 1,4 addition, which is Michael addition. Hard nucleophile undergo 1,2 addition. Sulfoxide nucleophiles are soft, so it attack on the fourth position. Charge travel, charge again travel back, form methylation at the third, fourth position. On the contrary, sulfur halides are hard, attack on the second position. It form O nucleophile. O nucleophile attacks. Methylation happen on the carbonyl. So two different set of methylation by two different set of reaction. The concept you outlined here is sulfoxide nucleophiles are soft, sulfur nucleophiles are hard. Then the next reaction, starting material is cyclohexane with epoxide and imine containing hydrogen. You are reacting with sodium ethoxide. You should find what will be the final product. By looking at the imine, you might realize it's a sapphiro-olefination reaction, but there is a difference in the reaction. First step will be proton abstraction. Proton abstracted, charge travel. Since the ring is strained full, the ring tried to open itself, so epoxide ring is opened. Then charge has to be quenched. Again the charge travel, you end up with alkyne triple bond and N2 and TS elimination. Finally you have unusual product. Here when compared to normal Sapporo reaction, different thing happened because of epoxide. The concept you outlined here is whenever you do naming reaction, always think the other possibility and the fundamentals. Then the next reaction, you have alkene. One side you have methyl group, another side you have methyl with silyl group. Silyl is stereochemically specified. Zinc copper couple you are using, methylene iodide you are using, and ether. You should find what will be the final product. By looking at zinc copper couple and diiodide, you might realize it's a Simon-Smith reaction. Basically, it's a cyclopropyl reaction. Basically, it's a methylation of alkene, but stereochemically different here. Only difference is stereochemistry, whether it form above the plane and below the plane. Since silyl group is bulkier, the attack should be expected on the back side because big group is above the plane. So the attack happen on small group side, which is hydrogen, which is below the plane. So attack happen, methylation occur, It is similar like Cramp's rule. Methylation happened below the plane. The concept we outline here is Smith reaction can be controlled by bulkiness of the nearby groups. Then the next reaction, here you have ketone, one side you have cyclopropene, another side you have propene, you are using sulfuric acid. You should find what will be the final product. The reaction is Nazarov cyclization reaction, basically dienone to cyclic conjugated ketone. To understand the reaction better, we should redraw the molecule for the cyclization. First step will be activation of carbonyl. So carbocation forms, then charge travels to quench the cation, then charge travels, cation shifted, finally end up with cyclic product enol and cation. Enol can become ketone through tautomerism. Then cation quenched by hydrogen end up with conjugated ketone. So basically the cyclization from dienone. The concept we outline here is you should master the delocalization mechanism and stability of intermediate. Then the next reaction, you have cyclopentene. Below the plane you have alkene as well as acid. You are using sodium bicarbonate and iodine. You should find what will be the final product. Here you are generating the internal nucleophile from acid, O- forms. Next step is iodination. Iodination can happen in the isolated alkene as well as ring alkene. Here ring alkene is favorable because of its static nature. Side chain alkene is always rotating. It could be the minor one. So final product also minor. On the contrary, the ring alkene leads to the final product. Then ring alkene, internal nucleophile attack. You have above the plane iodine. Here the important thing you should notice is ring rigidity and the ring size promote the favorable product. Then the next reaction, here you have Decline system with ketone and epoxide. You are using amine as the reactant. Dicline at high temperature you are using. You should find what will be the final product. The ketone is there, amine you are using, basically the hydrazine analog. So hydrazine formation is possible. So Sapporo elimination is possible. First step will be hydrazine formation. Then heating up leads to the ring opening. Then charge travels into elimination. Into elimination leads to the alkyne formation. The ring is open, ring will become macrocyclic. 10-member ring with alkyne and ketone. It's an unexpected product due to the ring opening. The concept we outline here is Sapporo elimination can go sideways if there is any intermediate or strain in the system. Then the next reaction, you have cyclohexenone, sodium borohydride and cetic chloride you are using, then metachlorobenzoic acid you are using. You should find what will be the final product. The reagent is called Luce's reagent, sodium borohydride and cetic chloride. It is selectively reduce the carbonyl, not the alkene. It's a chemoselective reduction. The reason is cerium can activate the carbonyl, promote the reduction. So the major is conjugated alcohol. Then peroxide you are using mean we end up with epoxide. Epoxide needs syn bond because both will form at the same plane. So final product is epoxide with alcohol. The concept we outline here is Luce's reagent selective to carbonyl, only reduce it into alcohol. Then the next example, you have alkene, alcohol on one side, acid on another side. You are using osmium tetroxide, then acidic hydrolysis. You should find what will be the final product. Here osmium tetroxide you are using, so alkene become diol. Since the attack on the same phase, both will get the same plane alcohol. So let us write above the plane. We have to rotate the molecule for the cyclization. If you rotate, one alcohol become trans there, so it get trans, alcohol and acid nearby. So the chances of ester formation, ester formed through the nucleophilic addition, then acid attacks, H2O eliminates. You have cation near the alcohol, then it is quenched as carbonyl there. So you start from acid and alcohol. It's intramolecular esterification reaction. Only difference is alcohol geometry. The concept you have to learn here is whenever you bend the molecule, you think of stereochemistry because rotation leads to the change in configuration. Then the next example, you have benzene with methyl and O-methyl group, lithium and liquid ammonia you are using. You should find what will be the final product. By looking at methyl and O-methyl, you might realize it's a Bitch reduction reaction, but where the regioselectivity happen, where the double bond form. Normally 1,4 double bond forms or 1,4 reduction happen, but the reduction happen away from electron donating group. Here both are electron donating, but O-methyl is stronger because of mesomeric in nature. Methyl is electron donating by inductive, O-methyl is by mesomeric. So the effect is stronger, so double bond cannot form nearby. So among the three possibilities, A is major, B and C are minor, because in B reduction happen near O-methyl, in C reduction happen near methyl. Both are electron donating, so reduction cannot be happen. So the reduction happen away from both, that is the A possibility, which is major. The concept you have to learn here is in Bitch reduction, regioselectivity is decided by the electronic effects. Then the next reaction, here you have linear molecule with isopropene on the end, alkene and the alcohol at the other end. You are using minus DET, titanium isopropoxide, tertiary butyl acid and dichloromethane. You should find what will be the final product. By looking at the DET, you might realize it is a sharp plus asymmetric epoxidation. Normally, the question is whether epoxide form above the plane or below the plane, and it is decided by the position of OH and DET you are using. If OH is on left side and DET is minus 1 mean epoxide form the plane. The table shows the 4 possibilities, but our case is minus DET and alcohol left mean above the plane epoxidation. Here oxidation is regioselective because 2 alkene is there, only the alkene near alcohol is oxidized become epoxide. The concept you have to learn here is sharp plus asymmetric epoxidation is distereoselective epoxidation decided by DET and OH position. Then the next example, you have cyclohexenone, methyl and isopropene present at the 1,4 position, isopropene below the plane. You are using lithium and ammonia. You should find what will be the final product. The reaction is basically a reduction. Lithium is electropositive, provide the electron. So lithium donate the electron travels, you have O minus. O minus is the nucleophile, it can abstract the proton, it become alcohol. Here alcohol is enol form, so it can become ketone by ketoenol tautomerism. The concept you have to learn here is chemoselective reduction. Even though 2 alkene is there, only conjugated alkene got reduced because of the selectivity of lithium and liquid ammonia. Here you should know that stereochemistry is given for the distraction. One additional fact you should know here is stereochemistry given here for distraction. Then the next example, here you have conjugated ketone which is cyclohexenone. You are using sodium borohydrate methanol, sodium borohydrate with cerium chloride. You should find what will be the final product. The reaction is all about chemoselectivity. Why? Because carbonyl is attacked or alkene is attacked. If you use just sodium borohydrate, the nucleophile is soft, it attacks the 1,4 addition. You can say Michael addition. Charge travels, it quench with H plus, become alcohol. The alcohol is enol, you end up with ketone there. So alkene is reduced. On the contrary, cerium chloride you are using mean cerium can activate the carbonyl. Reduction happen at the carbonyl. So 2 different reduction with 2 different reagents. The concept you have to learn here is chemoselectivity can be achieved by the choice of reagents. Then the next example, you have cyclohexanone, side chain you have ester, you are using lithium aluminum hydride and sodium borohydride. You should find what will be the final product. Here you have two carbonyl. Which carbonyl will be reduced is the real question. Sodium borohydride is the weak reducing agent because boron hydrogen bond is stronger because of boron electronegativity. So if you look at it, reactivity of ketone is stronger than ester because methoxide oxygen in ester reduce the electrophilicity by donation of lone pair. So only ketone is reduced. On the contrary, lithium aluminum hydride is reactive. It can reduce both the carbonyl, end up with no selectivity, reduce all carbonyl. So sodium borohydride selectively reduce the ketone. Lithium aluminum hydride reduce both the carbonyl. Then the next example, here you have butane, sodium and ammonia you are using as one set of reagent, and palladium and barium sulfate and hydrogen as the other set of reagent. You should find how it reacts with reactant differently. Here you have butane. At one set you are using palladium barium sulfate with hydrogen. The reduction happen. Alkyne become alkene by cis way. Why cis mean? Palladium is the metal. It can coordinate with alkyne. So hydrogen approach from same side. Reduction happen with same side leads to the cis alkene. On the contrary, sodium and ammonia you are using, it's a set mechanism. If you are interested, go and study separately. So radical anion form. To reduce the repulsion, anion rotate, form as the trans bond. Reduction happen in the trans way. So both generate the stereoselective reduction. Palladium barium sulfate generates cis alkene. Sodium ammonia can generate trans alkene. Then the next example, here you have linear chain compound with conjugated ketone. You are using borane with hydrogen peroxide and lithium aluminum hydride. You should find what will be the final product. Here two different reagents but the same reactant. It can create chemoselectivity. Here borane is selectivity to alkene because it's a electrophile. Electrophile cannot attack the carbonyl because carbon also possesses positive charge, positive repel, so it is not possible. So reduction happen with alkene, you end up with alcohol there. On the contrary, lithium aluminum hydride provide H- hydride anion. It cannot attack the alkene because same charges. Pi bond also pi electron cloud. H- also same charge, repel each other. So only possibility is carbonyl there. So the attack happen, you end up with alcohol. So two different alcohol formation with two different reagents. The concept you outline here is you should master the charges to master the organic chemistry. Then the next reaction. Here you have same compound cyclohexane with methyl isopropyl and chlorine. First compound chlorine above the plane, second compound chlorine below the plane. You are using the same reagent. You should find what will be the final product. Here strong base you are using, chlorine also a leaving group, so possibility of E2 elimination. So we should redraw the molecule with hydrogen. If you redraw it, you might realize the possibility of E2 elimination. The E2 elimination need anti-periplanar hydrogen. A pathway has only one hydrogen, which is second hydrogen. Removal leads to the alkene. On the contrary, on the B pathway, you have two hydrogen, which is P and Q, but major product will be the more substituted product, which leads to the Q hydrogen removal. You have the major product. The concept we outline here is E2 elimination require anti-periplanar position, plus it follows the sub pathway. Then the next reaction, you have pyrrole and pyridine. You are using bromine, ethyl alcohol in low temperature. The reagents are same in both cases, two different reactants. You should find what will be the final product. Here bromination is the basic possibility, but which will be reactive, which can form a nucleophile and electrophile, but Which will be the nucleophile and electrophile is the real question. In pyrrole, it's a normal aromatic compound. The attack happen on all possibility. Substitution in the ring happen. On the contrary, in pyridine, lone pair don't participate. It acts as a nucleophile, form NBR bond. That's why pyridine cannot undergo aromatic electrophilic substitution reaction, leads to the N substitution. So pyrrole undergo aromatic electrophilic substitution, pyridine undergo N substitution. Then the next reaction, you have pentane. Second and third position, you have bromine and methyl group. Bromine and ethyl are syn to each other, stereochemically given above the plane. You are using the strong base, sodium ethoxide. You should find what will be the final product. Here base you are using, chances of E2 mechanism. E2 mechanism need anti-periplanar position. So we should redraw with hydrogen and stereochemistry. Since above the plane is given, the hydrogen should be below the plane. If you redraw it, you can clearly see anti-periplanar elimination require rotation. If you rotate, you end up with transform. Because HBr elimination is anti, product also should be anti to each other. Finally, you end up with alkene there. Then the next example. Here you have cyclic compound with heterocyclic nitrogen, oxygen and carbonyl and isopropyl above the plane. In N substitution, it's amide with ethyl group. We are using LDA, benzyl bromide and lithium aluminum hydride. You should find what will be the final product. Here LDA you are using. LDA can abstract the proton, leads to the nucleophile. So nucleophile is N nucleophile. It can attack the benzyl bromide. We end up with new CC bond. Then lithium aluminum hydride you are using. Here the interesting case. The attack happen on below. Since isopropyl above the plane mean benzyl attack from below due to the steric reason. The stereochemistry is defined here. Benzyl below the plane. Lithium aluminum hydride, where the reduction happen is real question. A carbonyl or B carbonyl. A carbonyl is more reactive than B carbonyl because nitrogen and oxygen can reduce the electrophilicity of carbonyl. So A is more reactive. Reduction happen. You have side chain cleavage. End up with final product, which is alcohol with benzyl below the plane. The concept you outline here is regioselectivity. Here, even though you have two carbonyl, only A is reactive, B is not reactive because of mesomeric effect on nitrogen and oxygen, which can reduce the positive charge on the carbonyl. Then the next example, you have cyclohexane in chair form, 4-methyl group and alcohol in the system. You are using NOCl, light and HCl. You should find what will be the final product. By looking at the light and HCl, you might realize it is the Barton reaction. In Barton reaction, delta hydrogen transfer will take place. Here 4 delta hydrogen, but only one delta hydrogen is nearby, which is A1. Since the ring is rigid, other hydrogen cannot bend itself to the alcohol, so only A hydrogen transfer takes place. OH attacked by NOCl, which is NO bond formation, which promote the radical. In lighting condition, promote the radical. Then hydrogen transfer, you end up with radical and delta carbon. Then NO attacks, you have exchange of NO and hydrogen. Then NO is the enol, you can redraw to the oxide. Then HCl leads to the ketone there. The reaction technically called Barton reaction. Hydrogen transfer mainly taking place. Delta hydrogen is the important factor here. The concept he outlined here is, in Barton reaction, delta hydrogen should be on proper angle for the exchange with radical. Then the next reaction, you have dibromocyclohexane reacting with alcoholic KOH. You should find what will be the final product. Here you have dihalogen. Alpha position is acidic. Here you are using the strong base. Base can abstract the proton. Here many hydrogens are there, but only A hydrogen is abstracted. All other leads to the less probable product. You cannot abstract hydrogen near the bromine because of steric effect. So only alpha hydrogen can be abstracted. You cannot abstract again and again from the same one because sp2 carbon bromine hydrogen bonds are smaller. The carbon hydrogen bonds are smaller, difficult to eliminate. So only possibility is conjugation. That's what proposed here. First step will be A hydrogen abstraction leads to the anion. Anion quenched with bromine elimination form the alkene. In the same case, another set of hydrogen is abstracted. It form anion. It abstracts. You have conjugated alkene. The concept you outline here is continuous hydrogen abstraction from the same carbon is not possible because of change in hybridization. Then the next example. Here you have benzene, side chain you have ketone, another side chain in ortho position which contain halide. You are using methyl magnesium bromide and hydrogen, acidic hydrolysis and magnesium and acidic condition. You should find what the different reagents can make. Here two different pathways are projected, A and B pathway, different nucleophile, different ring size. Let us see one by one. In the A set of reaction, first step will be methyl magnesium bromide attack. It is a nucleophilic addition on carbonyl, leads to the O- nucleophile. O- attacks the chlorine, form a new ring, becomes 6-member ring. On the contrary, magnesium you are using, magnesium form Regnard reagent. Regnard reagent can generate the nucleophile, attacks the carbonyl, 5-member ring is formed. Finally, quenched with hydrogen, end up with alcohol. First set of reaction you have 6-member ring. Second set of reaction you have 5-member ring. Here only intramolecular mechanism is proposed. Why? Because intermolecular require collision. Intramolecular don't need of any collision. The concept you outlined here is you should always focus on nucleophile generation and attack on the electrophile. Then the next example, you have benzene, side chain you have ketone and ortho position you have halogen. You are using methyl magnesium bromide, acidic hydrolysis. You should find what will be the final product. Here you have carbonyl. You are using methyl magnesium bromide. It acts as a nucleophile, so nucleophilic addition on the carbonyl happened. So it formed new CC bond with O-. O- can act as a nucleophile. It attacks the chlorine carbon. It forms 6-member ring. If you redraw nicely, you have heterocyclic fused compound. You may wonder why intramolecular reaction happened rather than intermolecular mean. There is no collision of atoms required. Further, the atoms available readily. That's why intramolecular. The concept I outlined here is whenever there is a no quenching pathway, carbonyl oxygen can act as a nucleophile. Then the next example. Here you have 6-member heterocyclic compound with ketone, both sides like ketal architecture, both oxygens. You are reacting with methyl magnesium bromide and water. You should find what will be the final product. Here methyl magnesium bromide is there. It's a nucleophile. It provides CH3 nucleophile. It attacks the carbonyl. Oxygen is the good leaving group. It leaves quenched with H plus form alcohol. Again there is a possibility of carbonyl nucleophilic addition. Methyl magnesium bromide. Second molecule attacks. You have O nucleophile. As we discussed, oxygen is the good leaving group. You end up with ketone and diol. Then further methylation happen because as long as carbonyl available, addition is possible. It happened, you end up with tertiary alcohol. The concept we outline here is Grignard reagent reacts until the carbonyl groups available. Then the next reaction, you have 1-butyl reacting with metachlorobenzoic acid and methyl magnesium bromide. You should find what will be the final product. Here you are using metachlorobenzoic acid. It can oxidize the alkene, form epoxide. It's an oxidation reaction. It's an important reagent. Then methyl magnesium bromide can attack. The mechanism of ring opening is SN2 mechanism. So less hindered side will be attacked. So instead of attacking the second position, it attacks the first position. It is steric free. So the major product is ring open at the side chain. Further, O minus quenched with alcohol. If you redraw nicely, you end up with alcohol. The concept you have learned here is epoxy ring opening follows the SN2 mechanism. Then the next reaction, you have benzene attached with cyclohexane. Bromine and phenyl are stereochemically specified. Bromine above the plane, phenyl below the plane. You are using sodium hydroxide, heating it up. You should find what will be the final product. Here clearly the elimination reaction because heat promotes the elimination, but whether E1 or E2 reaction follows is the real question. So we comfortably eliminate the substitution reaction bromine to alcohol. Other one is E1 or E2. The elimination possibility here is the E1 because cation can be stabilized by phenyl. It can involve in the delocalization, can stabilize itself. So it forms dominantly. So E1 mechanism is favorable. Then hydrogen eliminates, you end up with alkene. The alkene also conjugation with benzene. That's also promote the final product. The concept you outline here is whenever there is a possibility of cation, E1 mechanism is the possible mechanistic pathway. Then the next reaction. Here you have epoxide with 2 methyl group. Methanol with acid is one reactant. Methoxide is the second reactant. You should find what will be the final product. Here epoxide is there. Epoxide can attack H+. Ring can open in either way. Ring can open A or B, but A break leads to the dominant product because stability of cation. So ring open, tertiary cation forms. Methoxide attack, you have the final product in acidic condition. On the contrary, Q, methoxide attack, the mechanism is SN2 mechanism. So the attack needs less steric side. The attacking possibility is A or B. A is steric, B is steric free. So B side attack happen, ring open, you end up with alcohol. Basically, you are playing with reagent, promote the regioselectivity. Then the next reaction, you have cyclopentanone. Second position, you have long chain acid. You are reacting with polyphosphoric acid. You should find what will be the final product. The molecule undergoes cyclization, so you redraw to the cyclic possibility. The polyphosphoric acid is the strong acid. It can abstract OH from acid. It forms acyl cation. Then you have acidic proton. Acidic proton can be abstracted because it's an active methylene group. So cation and anion combine each other, form spiro compound. If you read that nicely, you can clearly see 5-member spiro compound end up with diketone. The concept you outline here is polyphosphoric acid is the strong acid. Even it can form acyl cation with acids. Then the next example, here you have benzene, side chain you have bromine, methyl and isopropyl. Bromine and methyl are stereochemically specified. Bromine below the plane, methyl above the plane. You are heating it up 180 degrees Celsius. You should find what will be the final product. Here basically a E2 mechanism. Problem is the position of hydrogen. Since you don't have hydrogen at anti-periplanar position because E2 elimination demand anti-periplanar position for HBr elimination. Here I drawn with conformation, bromine and hydrogen given as syn to each other. So you redraw the molecule with rotation. The conformation become anti. Then if you do elimination, you have reversed configuration of alkene. Here rotation is important because you are changing the configuration. Isopropyl group going from above to below. It is end up with cis configuration or you can say technically Z configuration. The concept you outline here is whenever you rotate the carbon, always you should analyze configuration. Then the next example, you have dichloroethane. you are converting into cyclohexene, you should find the reagents and number of steps involved in the organic conversion. Here I given one possible reaction pathway. Here you are using sodamide, strong base, promote the elimination, form the alkene. Again the second mole of NaNH2 you are using mean form alkyne. So alkyne you reduce into double bond by sodium and ammonia. Finally form alkene. You want cyclohexene. So if you do Diels-Alder reaction, you end up with diene and dienophile situation. Finally cyclohexene form. Whenever you see isolated alkene, you might think of Diels-Alder reaction. The concept you have to learn here is to master the organic conversion, you should master the naming reactions. Then the next reaction, you have long chain molecule with alkene, bromine at the side chain. You end up with 6-member compound with oxygen, which is heterocyclic ring. You should find reagents and number of steps involved in the conversion. The final product is cyclic compound. So you redraw the molecule for cyclization possibility. So the first step will be hydroboration reaction because you will end up with terminal alcohol. It's anti-Markovnik of addition. So OH attached with terminal position. If you use the base abstract the proton, oxygen become nucleophile. So it attacks the carbon, bromine elimination occur, you end up with desired product. If you redraw nicely, you get the proper ring formation. The concept you have to learn here is to master the organic conversion, you should master the rules. Then the next example, here you have fused system. One side you have cyclohexane, another side you have lactone, iodine and hydrogen below the plane. You are using sodium hydroxide. You should find what will be the final product. Here the problem in the plane side. If you redraw the molecule with hydrogen, you can identify the proper reaction pathway. Because base promote the elimination reaction. Here hydrogen is the leaving group. So HI elimination is the major product. So A, B, C 3 possibilities, 3 hydrogen. Among that C hydrogen elimination is minor because elimination require anti-periplanar position. Here C hydrogen and iodine is syn to each other. Then you have B hydrogen elimination, that is the major product. Then you have A hydrogen elimination. It is the minor product because it don't have any extra stability. If you look at the B, it is the major product. Why? Because hydrogen is anti. It forms conjugation with ketone. So the final product could be much better than A and C hydrogen elimination. The concept you have to learn here is whenever you do organic conversion, you should know all stabilizing factors. Then the next reaction. Here you have linear chain compound with terminal dibromine. You should find what will be the final product. Here long chain is there, chances of cyclization. So we redraw the molecule for cyclization. First step will be attack of nucleophile on bromine carbon. Amine is the nucleophile. It attacks, you have NC bond. Then amine can be an internal nucleophile. It attacks again, forms cyclic quaternary amine. If you do hydrogen elimination, you end up with cyclic piperidine with N-methyl group. Here you may wonder why the intramolecular reaction, not the intermolecular reaction mean. Cyclic products are more stable than linear chain, as well as intramolecular reaction don't require any collision, so it is favorable and it has readily available atom inside the molecule. The concept you have to learn here is always you conduct the reaction until the functional groups are available. Then the next reaction. Here you have amine. Side chain you have chlorine and methyl group. You are using potassium hydroxide and water. And second reaction, instead of methyl group, amine substituted with phenol. You should find what difference it can make in the final product. Here basically a neighboring group participation reaction because amine can assist the chlorine elimination. First set of reaction, amine assists, chlorine leaves, finally you have substituted product. On the contrary, B pathway, chlorine eliminates itself, form cation. Then the cation switches, it converted into stable cation, finally attacked by OH minus, end up with alcohol. Here neighboring group assistance is not possible. Why? Because the lone pair participate in the delocalization. It is not available for the assistance. So A pathway leads to the terminal alcohol. B pathway leads to the substituted medyl alcohol. The concept we outlined here is for neighboring group participation, electron density of the donating atom is crucial factor. Then the next reaction, you have cyclohexane, chlorine, iodine, acid in the substitution. You have to convert it into cyclohexane and find reagents and number of steps involved in the organic conversions. Here starting material to product mean you have to remove all functional group. First step easy will be removal of chlorine because you substitute with iodine. Iodine can attack, it form diiodide. If you use the heat, iodine is the good leaving group, so it leaves, it form alkene there. Carboxylic acid can be removed by the same heat. For convenience, I shown as a two steps. Carboxylic acid removes CO2, end up with cyclohexene. Alkene can be converted into alkane by palladium and hydrogen. You end up with desired product, cyclohexane. The concept we outlined here is you should master the leaving group ability as well as nucleophilicity in the organic conversion reaction. Then the next reaction, you have cyclohexenone. Third position, you have O-methyl group. You are reacting with phenyl magnesium bromide in acidic condition. You should find what will be the final product. Here you have phenyl magnesium bromide. It's a hard nucleophile. It can attack the carbonyl. So 1,2 addition happen, not the 1,4 addition, which is Michael addition. Hard nucleophile leads to 1,2 addition. It attacks, you have phenyl with alcohol. Then alcohol in the acidic condition means alcohol will remove because oxygen lone pair can assist the leaving. So oxygen lone pair participates, double bond migrate. You end up with conjugated ketone in the unusual way. Here neighboring group participation produce the unusual product. The concept we outlined here is hard nucleophile undergo 1,2 addition. Then the next example, you have cyclohexane, one side alcohol, one side tertiary butyl group. You are reacting with chromium oxide. Two set of reaction given. One is cis relation of functional group, another is trans relation of functional group. You should find kinetics of B is higher than A and you should know why. Here the problem can be easily understood by drawing in the chair form. So we redraw to the chair form. One is alcohol above the plane, another is below the plane. Here if you look at it, cis relation, alcohol above the plane means the steric hindrance is very high. So what really happened? Chromium will oxidize the alcohol, immediately free the steric effect because of sp2 carbon. It is 120 degree planar, trigonal planar structure. So it can form quickly because it has steric assistance. The A don't have any such support because already it is steric free. So the kinetics of B is always higher than A due to the steric effect. The concept we outlined here is even the negative effects can drive the kinetics of the reaction. Then the next example, you have benzene, dimethyl group in 1,2 position. You are using sodium ethyl alcohol, liquid ammonia. You should find what will be the final product. Here if you look at the benzene and liquid ammonia, you might realize it's a Bitch reduction reaction. It's a regioselective reduction because double bond can form away from the electron donating group because reduction cannot happen near the electron donating group. The same charges repel each other. That's why reduction happen away. The starting metal is symmetrical, so only two possibilities A and B. B has the possibility because double bond form away from at least one methyl group. So it is the major product. If you are interested, go and study mechanism separately. It's a very important naming pitch reduction reaction. The concept you outlined here is pitch reduction is regioselective reaction. Double bond form away from electron donating group. Then the next example, you have linear compound with dialkene and alcohol. You are using plus DET, titanium isopropoxide, peracid, dichloromethane. You should find what will be the final product. Here by looking at the DET and enol, you might realize SAR plus asymmetric epoxidation. It is a diastereoselective epoxidation. You should find epoxidation happen above or below the plane. Here the whole product is controlled by position of OH as well as DET. If DET above the plane, if DET is plus, alcohol left the plane mean you have below the plane epoxidation. This table guide you to the final product. Only you have to find DET and alcohol position. Here one more thing you should notice is chemoselectivity. Since there is two alkene, only one alkene is reacted because of OH coordination. So it's a chemoselective, or you can say regioselective here also because both are alkene. So final product is below the plane epoxide. The concept you outlined here is in SAR plus asymmetric epoxidation controlled by alcohol position as well as DET. Then the next reaction, here you have phenandrine converting into a less aromatic compound. Middle ring become OH and COOH. You should find reagents and number of steps involved in the reaction. Normally middle ring is very weak, B ring is very less aromatic because of annihilation effect. Annihilation means partial aromatic. A and C ring are individually aromatic, B is less aromatic, so it can be reacted. So chromium oxide you are using mean alkene become diketone. There is a possibility of benzylic acid rearrangement. So OH minus can attack, form new carbon oxygen bond. Then charge travel, ring contracted. You have 5-member ring with O minus. Then O minus quenched with alcohol. If you redraw nicely, you have desired product. The concept you outlined here is middle ring of phenandrine is weak because of annihilation effect. Then the next example, you have cyclic compound with heterooxygen, chlorine below the plane, sulfur above the plane, sulfur attached with acyl ketone. You are using lithium aluminum hydride. You should find what will be the final product. Here you are using lithium aluminum hydride. Among the many functional group, carbonyl is polar here. So it readily reacts. The reduction happen at carbonyl. Nucleophilic addition of H minus and carbonyl leads to the O minus. O minus has to be quenched. So O minus travel, you end up with S minus. Then S minus can be a nucleophile. Chlorine is the good leaving group. It attacks, you end up with epoxide analog of sulfur. Here many things happening. One is chemoselectivity. First step, lithium aluminum hydride only attacks the carbonyl. Reaction continues until the functional groups, and there are many leaving group and functional group. So the reaction continues until the functional groups are available. In the same way, reaction continues until the leaving groups are available. Then the next example, here you have cyclic compound with one bridged carbon, two methyl group, alkene and methyl group. You are reacting with boron, hydrogen peroxide and base. You should find what will be the final product. Here the reaction may look simple hydroboration, but it involves stereochemistry. Since the bulky group on the bridges, attack happened from the below. So the attack happened below. It's the first stereoselectivity where the BH2 attack. BH2, as we know, it form anti-Markovnikov product. It is a regioselectivity. So stereoselectivity as well as regioselectivity here end up with final below the plane alcohol. One additional factor is bromine and hydrogen syn to each other because addition is syn addition. The concept you outlined here is you should study even a simple reaction with deep understanding, then only you can predict the final product with stereochemistry.